the inscription, "Here lies Salvino Armato d'Armati of Florence, inventor of spectacles. May God pardon his sins. A.D. 1317. In the tall lighthouses that today guard the coast of every civilized country is found the peculiar echelon or annular lens, to avoid the spherical aberration and the loss of light inevitable in refractors of such magnitude as those of the lighthouse lights. These lenses are made in concentric rings of glass, which focus in one point, the outermost ring being some 2 feet in diameter. The light placed in this focus is not too widely distributed and becomes brightly visible over a distance of more than 40 miles. Some conception of the power of these lenses may be had from the fact that when inverted and used to condense the solar rays, gold, platinum, and quartz are melted in the intense heat, and less refractory substances, as lead, tin, and zinc, are almost immediately reduced to vapor. Far more perfect than any previously produced were the glass lenses made in Munich by Josef Fraunhofer. The talented son of a poor glazier, Fraunhofer combined a thorough practical skill with an unusual degree of theoretical insight. By his invention of new and improved methods, machinery and measuring instruments for grinding and polishing lenses, by his having the superintendence, after 1811, also of the work of glass melting, enabled him to produce flint and crown glass in larger pieces, free of veins, but especially by his discovery of a method of computing accurately the forms of lenses, he has led practical optics into entirely new paths, and has raised the achromatic telescope to a perfection hitherto undreamed of. So writes Lommel in his preface to Fraunhofer's Gesammelte Schriften. Among the many other applications of the lenses which have made a necessary place in present-day life, the camera deserves especial notice. Battista Porta, a Neapolitan physician and contemporary of the great Gilbert, invented an instrument now familiar enough to every schoolboy of a practical turn of mind, the camera obscura. A simple box, light-proof, and painted black within and without, received through a lens the image of external objects, and reflected it from a sloping white paper sheet onto a pane of ground glass in the top of the box, to imitate in the form of a fixed photograph. The beautiful colored image thus thrown on the plate, subsequent artists and scientists have sought in vain. The color photography thus far accomplished has been a complicated and difficult procedure, rewarded by only partial success. The camera obscura may hardly be considered the antecedent of the photographic camera of today, which resembles the pinhole camera in structure more nearly. Yet the essential principle of the modern camera was not different from that of the camera obscura. With an adjustable or focusing lens, and the substitution of a sensitive film or plate for the former plate of ground glass, the transformation was accomplished. In modern days, many people take photographs, and there is more or less familiarity with the nature of the chemical changes that are worked by the exposure to the light of the silver salts upon the sensitive plate. If exacting reason, however, demand in this connection an explanation of why the change takes place, it must be answered in brief that the energy of the light ray probably effects a rapid alteration of the structure of the atoms of the silver salt employed, in much the same way as has been noted before in the different forms of copper and iron. When the velocity of waves of light is remembered, it becomes clear that a 1/10 second exposure means that these atoms have been hammered thousands of times by light waves in that brief period. The art of photography is of very recent development, depending of necessity upon a certain advance in the science of chemistry. Pictures on metal were produced in 1827 by Joseph Nicephore Niepce, whose assistant and successor in this work, Daguerre, has given his name to the improved metallic photographs, which are still called after him daguerreotypes. These first attempts at a photograph were clumsy contrivances, requiring from 5 to 7 minutes exposure, during which the photographee must sit with iron face and rigid figure, immovable. The face of the sitter had also to be dusted with white powder, and the print, when completed, was faint and in certain lights invisible, on account of the brilliant polish of the metallic surface upon which the print was made. Tinting the picture was commonly resorted to in the endeavor to make the results more lifelike. From the slow and troublesome methods of the old daguerreotype to the magnificent black and white instantaneous carbon prints of today is a long stride. It frequently happens in human history that after an invention has been made and perfected, the further progress of knowledge reveals the fact that the wonderful invention already existed in nature in a state of development far more advanced. The old scoop dredge, though it still has its special use, has been largely replaced by a huge iron hand, like a man's hand. The phonograph is a clumsy imitation of the auricular nerve and the tympanum of the human ear. The eye has been described as a camera with a self-adjusting shutter and focusing automatically. Without going too minutely into the physical structure of the eye, its essential parts may briefly be summed up. Covering all the exposed front of the organ is a tough, elastic membrane, cornea, which lets through the light, but protects the delicate mechanism immediately behind. This interior part it is which lends character and color to the eye, the iris or colored ring appearing of various hues, as ranging from light gray blue, which is largely destitute of the orange-brown coloring pigment, to a brown so deep as almost to seem black. Helmholtz, writes Cajori in his history already referred to, irreverently disclosed the fact that in blue eyes there is no real blue coloring matter whatever. The deepest blue is nothing but a turbid medium. The optic action is the same as in the case of smoke, which appears blue on a dark background, though the particles themselves are not blue, or in the case of the sky, which, according to Newton, Stokes, and Rayleigh, appears blue through the agency of extremely fine dust suspended in the air. This dust, when illuminated by sunlight, reflects a greater proportion of the shorter waves of bluish light and transmits a greater proportion of longer waves of reddish light. The pupil of the eye is the shutter, which, by the expansion or contraction of the iris, lets in more or less light to the sensitive film or retina at the back of the organ. Close behind the pupil and its encircling iris, the crystalline lens reflects incident light from objects near or remote, and by the aid of the enveloping ciliary muscle, may be so far contracted as to focus the vision with equal readiness upon a tiny shell in the hand or a mass of rocks on a far distant mountain. Through the glassy liquid which fills all the remaining interior of the eye, the light is transmitted to the retina, where a chemical change is constantly being effected upon the exposed film of this optical photographic camera, the optic nerves reporting to the brain at every moment the nature of these changes. With all its beauty and delicate adjustment, however, the human eye has many imperfections. No voice has spoken of the physics of the eye with more authority than has the extraordinarily versatile and learned Helmholtz. To him the eye is indeed a crude instrument. The German physicist indicates its defects with considerable force. A refracting surface which is imperfectly elliptical, he says. An ill-centered telescope does not give a single illuminated point as the image of a star, but according to the surface and arrangement of the refracting media, elliptic, circular, or linear images. Now the images of an illuminated point, as the human eye brings them to focus, are even more inaccurate. They are irregularly radiated. The reason of this lies in the construction of the crystalline lens, the fibers of which are arranged around 6 diverging axes, so that the rays which we see around stars and other distant lights are the images of the radiated structure of our lens, and the universality of this optical defect is proved by any figure with diverging rays being called star-shaped. It is from the same cause that the moon, while her crescent is still narrow, appears to many persons double or threefold. Now it is not too much to say, he remarks again, that if an optician wanted to sell me an instrument which had all these defects, I should think myself quite justified in blaming his carelessness in the strongest terms, and giving him back his instrument. The mechanical process of the eye has never, until comparatively recently, been understood. Helmholtz and others, basing their experiments upon the observations of Thomas Young, Louis Joseph Sanson, and Max Lagenbeck, have explained the manner in which the eye focuses and the means employed to control the admission of light. The sense of color, however, is still a matter of controversy. The most acceptable theory of color sense is that promulgated by Young and developed by Helmholtz, based on the phenomenon of color blindness to the three shades, which occupy respectively the ends and the center of the prismatic ribbon, namely red, green, and violet. Color blindness to red is common and to green not uncommon, while the inability to recognize violet is known. Young showed that the rotation of colored discs of red, green, and violet produces the impression of gray. These, therefore, may be taken as the three primary colors, by combination of which all the intermediate colors may be produced. End of section 11.
Section 12. The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Physics, Chapter 7, The Nature of Light, Part 1. To the phenomenon of total reflection was added in the very beginning of the 19th century another bit of evidence which the exponents of the corpuscular theory of light found difficult to explain away. This was the phenomenon of interference. Two plates of glass, touching at one end and separated at the other by a fine hair, will form between them a thin wedge of air. If a bright light is held near the plates, they will be seen crossed with dark and bright bands. Thomas Young, a brilliant young English physicist, experimenting with these plates and studying the dark bands, stated in a famous paper on light that they were due to the interference of light waves from the two surfaces of the wedge of air included between the plates of glass. He showed how the waves of light from these two surfaces might be proved to meet at intervals and produce the appearance of darkness, just as two sound waves may be combined to produce silence. This remarkable paper, by far the most valuable contribution to the study of optics since the time of Newton, attracted no favorable attention, and was received with open scorn and contempt by the editor of the Edinburgh Review. The young scientist is represented by this illustrious organ as deficient in the powers of solid thinking, and his theories dismissed as feeble lucubrations without any traces of learning, acuteness, or ingenuity. John Tyndall, that great and fascinating Irish scientist, writes of Young, "For 20 years this man of genius was quenched, hidden from the appreciative genius of his countrymen, deemed in fact a dreamer through the vigorous sarcasm of a writer who had then possession of the public ear." To the celebrated Frenchmen Fresnel and Arago he was first indebted for the restitution of his rights. The soundness of Young's reasoning has been abundantly attested to by the verdict of later investigators, and the known fact of the interference of light is today held to be one of the compelling arguments in favor of light as a form of vibration. Difficult of explanation as the fact of interference proved, from a corpuscular basis, still more did prismatic dispersion prove itself an occasion of falling. Everyone is familiar with the beautiful color effects obtainable with the aid of a triangular prism of glass, and has noted how a beam of white light may be spread out in a band of colors as the ray is bent through the prism. In this spreading out, it is evident that some of the rays are bent more than others. Unless the corpuscles of light were infinite in variety, this would be simply inexplicable as a corpuscular phenomenon. The prism as an instrument of optical study found its first great master in Isaac Newton. The observation of its effects had been noted by the Roman philosopher Seneca, and in the period of the Renaissance, the breaking up of white light into colors was discussed by Grimaldi, Descartes, Hooke, and others. But it required the supreme genius of Newton to make clear the true idea of the dispersion of light. With rough appliances fashioned by his own hands, he conducted his experiments. In his treatise on optics, he quaintly remarks, "I procured me a triangular glass prism, to try therewith the celebrated phenomena of colors, and in order thereto, having darkened my chamber, and made a small hole in my window shuts to let in a convenient quantity of the sun's light, I placed my prism at his entrance, that it might be thereby refracted to the opposite wall." He goes on to say how surprised he was to find that the ray of light, after passing through the prism, instead of being thrown upon the wall in the form of a round spot, was spread out into a beautiful colored ribbon, or spectrum, red at one end, yellow in the middle, and bluish-green at the other end. Comparing the length of this colored spectrum with its breadth, he continues, I found it about 5 times greater, a disproportion so extravagant that it excited me to a more than ordinary curiosity of examining from whence it might proceed. Then I began to suspect whether the rays, after their trajection through the prism, did not move in curved lines, and according to their more or less curvity, tend to diverse parts of the wall, and it increased my suspicion when I remembered that I had often seen a tennis ball struck with an oblique racket describe such a curved line, for a circular as well as a progressive motion being communicated to it by that stroke, its parts on that side where the motions conspire must press and beat the contiguous air more violently than on the other, and there excite a reluctancy and reaction of the air proportionably greater. And for the same reason, if the rays of light should possibly be globular bodies, and by their oblique passage out of the medium into another, acquire a circulating motion, they ought to feel the greater resistance from the ambient ether on that side where the motions conspire, and thence be continually bowed to the other. But notwithstanding this plausible ground of suspicion, when I came to examine it, I could observe no such curvity in them. And besides, which was enough for my purpose, I observed that the difference betwixt the length of the image and the diameter of the hole through which the light was transmitted was proportionable to their distance. The gradual removal of these suspicions at length led me to the experimentum crucis, which was this. I took 2 boards, and placed one of them close behind the prism at the window, so that the light might pass through a small hole made in it for the purpose, and fall on the other board, which I placed at about 12 feet distance, having first made a small hole in it also for some of that incident light to pass through. Then I placed another prism behind the second board. On turning the first prism about its axis, the image which fell on the second board was made to move up and down upon that board, so that all its parts could successively pass through the hole in that board and fall upon the prism behind it. The places where the light fell against the wall were noted. It was seen that the blue light, which was most refracted in the first prism, was also most refracted in the second prism, the red being least refracted in both prisms. And so the true cause of the length of that image was detected to be no other than that light is not similar or homogeneal, but consists of difform rays, some of which are more refrangible than others. No more complete or illuminating explanation of the nature of light through the agency of the prism has ever been given than this. Newton showed here the real reason of the dispersion, adducing the analogy of the rainbow, although he clung through it all to the corpuscular theory, postulating the existence not only of the flying particles constituting light, but also of an ether, all the mechanism, in fact, needed for the wave theory and more. It was not until the beginning of the present century that this experiment of Newton's, repeated as it had been in the meantime by many philosophers, was found by Dr. Wollaston to possess certain peculiarities which defied all explanation. He found that by substituting a slit in the shutter of the darkened room for the round hole which Newton had used, the spectrum was intersected by certain dark lines. This announcement, although at the time it did not excite much attention, led to further experiments by different investigators, who, however, vainly endeavored to solve the meaning of these bands of darkness. It was observed by the great Munich optician that they never varied, but always occupied a certain fixed position in the spectrum. Moreover, he succeeded in mapping them to the number of nearly 600, for which reason they have been identified with his name as Fraunhofer lines. It was one of the greatest contributions to science. Accidentally, he discovered in the spectrum of a lamp the double line in the orange, now known as the sodium line. He was endeavoring at the time to determine how the refraction through the glass would take place for different colored lights. The observation of the sodium line was a chance incident of his experiments. In oil and tallow light, and in fact in all firelight, he saw this same bright, sharply defined double line quote, exactly in the same place and consequently very useful. Examining the spectrum of sunlight cast through a small telescope upon a prism, he remarked, an almost countless number of strong and feeble vertical lines, which, however, were darker than the other parts of the spectrum, some appearing to be almost perfectly black. He also examined starlight with his primitive spectroscope and found many of the solar lines in the spectrum of the planet Venus. For nearly 40 years, the scientific world, absorbed in theories concerning the nature of light itself or the newly announced atomic theory of Dalton and the laws of chemical combination and composition, failed to see the meaning and significance of this discovery of Fraunhofer. The great astronomer John Frederick William Herschel, the electrician Wheatstone, William Henry Fox Talbot, Sir David Brewster, and others remarked on various similar phenomena in spectral experimentation, but none succeeded in finding the clue to the mystery. Many famous men between 1850 and 1860 turned their attention to this riddle. Herschel pointed out that metals, when rendered incandescent under the flame of the blowpipe, exhibited various tints. He further suggested that as the color thus shown was distinctive for each metal, it might be possible by these means to work out a new system of analysis. Bunsen and Kirchhoff in 1860 discovered that each metal, when in an incandescent state, exhibited through the prism certain distinctive brilliant lines. They also found that these brilliant lines were identical in position with many of Fraunhofer's dark lines, or to put it more clearly, each bright line given by a burning metal found its exact counterpart in a dark line on the solar spectrum. It thus became evident that there was some subtle connection between these brilliant lines and the dark bands which had puzzled observers for so many years. Having this clue, experiments were pushed on with renewed vigor until, by happy chance, the vapors of the burning metals were examined through the agency of the electric light. That is to say, the light from the electric lamp was permitted to shine through the vapor of the burning metal under examination, forming, so to speak, a background for the expected lines. It was now seen that what before were bright bands on a dark ground were now dark bands on a bright ground. This discovery of the reversal of the lines peculiar to a burning metal, when such metal was examined in the form of vapor, led to the enunciation of the great principle that vapors of metals at a lower temperature absorb exactly those rays which they emit at a higher. To make this important fact more clear, suppose that upon the red-hot cinders in an ordinary fire grate is thrown a handful of saltpeter, also called nitrate of potash or more commonly niter. On looking through the spectroscope at the dazzling molten mass thus produced, instead of the colored ribbons which the sunlight gives, all is black, with the exception of a brilliant violet line at the one end of the spectrum and an equally brilliant red line at the other. This is a spectrum peculiar to potassium, so that if not previously aware of the presence of that metal, and if requested to name the source of the flame produced, the spectroscope would have enabled such answer without difficulty. Now suppose this burning saltpeter to be again examined under altered conditions. Place the red-hot cinders in a shovel and remove them to the open air, throwing upon them a fresh supply of the niter. If the vapor now be examined while the sunlight forms a background to it, it will be seen that the two bright-colored lines have given place to dark ones. This experiment will prove the truth of Kirchhoff's law so far as potassium is concerned, for the molten mass first gave the bright lines, and afterward, by examining the cooler vapor, it was evident that they were transformed to bands of darkness. In other words, they were absorbed. The simple glass prism as used by Newton, although it is the parent of the modern spectroscope, bears very little resemblance to its gifted successor. The complicated and costly instrument now used consists of a train of several prisms through which the ray of light under examination can be passed by reflection more than once. By these means, greater dispersion is gained. That is to say, the resulting spectrum is longer and consequently far easier of examination. Since the middle of the 19th century, the analytical eye of this wonderful instrument has looked into the material universe and aided the chemist to the discovery of elements previously unsuspected and unknown. It has shown the composition of sun and stars by the correspondence of their spectra with those of terrestrial matter, to be in general identical with that of the Earth. Nor are its services to be measured merely in qualitative units, for in examining incandescent bodies, by a careful study of the absorption lines, a very exact estimate of the quantity present can be arrived at. This method of analysis is so delicate that in experiments carried on at the Mint, a difference of 1/10,000th part in an alloy has been recognized. Neither must it be supposed that the surfaces of the spectroscope are confined to metals, for nearly all colored matter can also be subjected to its scrutiny. Even the most minute substances, when examined by the microscope in conjunction with the prism, show a particular spectrum by which they can always be identified. While the spectroscope succeeded in proving that a certain yellow flame was the flame of sodium and a certain reddish flame was that of calcium, it did not show why the flame of one kind of substance should be brighter than another. The flame of burning wood, for instance, is less bright, generally speaking, than that of a burning kerosene lamp. The flame of phosphorus burning in oxygen is dazzling in its brilliancy. A ribbon of the metal magnesium, commonly used as a powder in flashlight photographs, burns in ordinary air with an intensely brilliant white light. The brightness of these flames cannot be due wholly to temperature, as has often been maintained, for there may be a solid such as iron or carbon burning in oxygen at a high temperature with brilliant incandescence or glowing but without flame, while on the other hand the lambent flame of boric methide or of camphor shows that flame may exist without a high temperature. A piece of burning camphor, in fact, may easily be held in the unprotected palm by changing it from hand to hand, a trick sometimes resorted to by stage jugglers. Again, the ordinary Bunsen burner found in every chemical laboratory will produce, by adjusting the air supply, either a yellow luminous flame of relatively low temperature or a much hotter non-luminous flame. whereas the temperature in the exceedingly brilliant electric arc is extreme, reaching in the electric furnace as high as 3,000 degrees centigrade. The real nature of flame was long a matter of conjecture. The phlogiston, fire substance of the 18th century, in fulfillment of the hope expressed by that erratic genius Count Rumford, is today interred, it is true, in the same tomb with caloric heat substance. But the death of phlogiston did not bring with it the explanation of the luminosity of flame. Sir Humphrey Davy, inventor of the Davy safety lamp, regarded the luminosity as due to the incandescence of solid particles suspended in the flame, and his theory, until about the middle of the 19th century, went unchallenged. The presence of solid particles, either in the flame itself or in immediate contact with the burning gas, was held to be essential. There is no doubt that the introduction of solid particles in a fine state of division into a flame of feeble luminosity will usually impart to it a considerable degree of brilliancy by the incandescence of the solid particles, or perhaps in some cases by reflection of the light from their many surfaces, and it is usual to refer to the black deposit, which is formed upon a glass rod or similar body when held in the flame of a candle or gas, as a proof that such flames contain solid particles. Nevertheless, luminous effects have been produced where the solid particle hypothesis could not account for them. Such, for example, as the luminosity of the flame of hydrogen burning in oxygen under pressure. Moreover, in many of the brightest flames, the temperature is such that fuliginous matter could not exist in them. In many cases, it seemed therefore to be a more satisfactory explanation that the luminosity of flames depends on the existence of a comparatively high temperature and on the presence of gases or vapors of considerable density. End of section 12. Section 13. The Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3. Edited by Francis Rolt Wheeler. Physics, Chapter 7. The Nature of Light, Part 2. The effect of high temperature is seen in the greater brightness of the flames of sulfur, phosphorus, and indeed all substances when burned in pure oxygen, as compared with the result of their combustion in air. Direct evidence of the effect of high temperature is also afforded by the combustion of phosphorus in chlorine, for while at ordinary temperatures only a feeble light is produced by this combustion, strongly heated phosphorus vapor burns in hot chlorine with a dazzling white light. A comparison of the relative densities of gases and vapors shows that the brightest flames in general are those which contain the densest vapors. Hydrogen burning in chlorine produces a vapor more than twice as heavy as that resulting from its combustion in oxygen, and the light produced in the former case is stronger than in the latter. Carbon and sulfur burning in oxygen produce vapors of still greater density, and their combustion gives a still brighter light. Phosphorus, also which has a very dense vapor and yields in burning a product of great vapor density, burns in oxygen with a brilliancy almost blinding. The luminosity of a flame is increased by compressing around it the surrounding gaseous atmosphere, and it is diminished by rarefying it. Thus, mixtures of hydrogen and carbonic oxide with oxygen emit but little light when they are burnt or exploded in free air, but exhibit intense luminosity when exploded in closed vessels, so as to prevent expansion of the gases at the moment of combustion. The density, then, of the gases formed in combustion and the temperature at which combustion takes place were thus held, by some physicists, notably E. Franklin, to be the sole determining factors in the brilliancy of a flame. As for the particles of solid matter, it is known that while in some instances they may increase the luminosity, in other cases they produce the opposite effect, rendering the flame less bright. All these known facts were thought during the latter half of the 19th century completely to have disposed of the solid particle idea in the brightness of flames. As a matter of fact, it is evident that the dense vapor theory, advocated by E. Franklin and others, while it adds much interesting information to what already is known of the nature of flame, does not in the least disprove the fact that a flame is bright when it contains particles of solid glowing carbon, and it is not luminous when it does not. Such brilliant and thorough investigators as Heumann, Birch, Smittels, Techa, and especially Vivian B. Lewis established the fact toward the end of the century that in the burning of ordinary illuminating gas, that remarkable illuminant acetylene is first formed and subsequently decomposed. Lewis' careful experimentation showed that in the dark part of the flame there occurs a transformation of gases, and that at the point where luminosity just begins, 70 to 80% of the compounds formed is acetylene, and this in a gas flame in which less than 1% of acetylene is originally present. Immediately above this point, the increasing heat of the flame breaks up the acetylene gas into its two constituents, carbon and hydrogen. The hydrogen burns in contact with the oxygen of the air. The carbon is heated to incandesce by the combined influence of the burning hydrogen and the so-called latent heat of the chemical separation, hence the flame. The real nature of flame is even today very commonly misapprehended. A popular idea exists that wood burns. Wood, strictly speaking, does not any more burn in air than it floats in water. The flames seen burning at the surface of a wood fire are due to the combustion of volatilized solid material, and their luminosity is generally conceded today to be due, as above shown, to the presence of finely divided particles of glowing carbon. Dr. Percy has accurately denned flame thus: ordinary flame is gas or vapor of which the surface, in contact with atmospheric air, is burning with the emission of light. This definition leaves little to be desired, for it very properly directs attention to the gas or vapor necessary to a flame, as well as to the fact that the flame itself is hollow. Dr. Robert Montgomery Bird has summed up the essential teachings of modern study of flame briefly as follows. When the hydrocarbon gas leaves the jet at which it is burned, those portions which come in contact with the air are consumed and form a wall of flame which surrounds the issuing gases. The unburnt gas in its passage through the lower heated area undergoes a number of chemical changes, brought about by the heat radiated from the flame walls. The principal change being the conversion of hydrocarbons into acetylene, hydrogen, and methane. The temperature of the flame rapidly increases with the distance from the jet and reaches a point at which it is high enough to decompose acetylene into carbon and hydrogen with a rapidity almost that of an explosion. The latent heat so suddenly set free is localized by the proximity of carbon particles, which by absorbing it become incandescent and emit the larger part of the light given out by the flame, although the heat of combustion causes them to glow somewhat until they come into contact with oxygen and are consumed. This external heating gives rise to little of the light. There have been opponents to his theory of the cause of luminosity, as there are, fortunately, of all theories, but the evidence is so strong and covers so many points, and so many investigators have confirmed one part or another of the work, that it has been generally accepted as a true statement of the facts with which it deals. Visible light, as Fraunhofer long since pointed out, reaches the eye in vibrations numbering from 4,000 to 7,000 billion per second. No other vibrations are useful to us for seeing purposes, for no others have any effect upon the retina of the eye. The analysis of the apparently white light of the sun and the combining of the spectral colors so formed to reproduce white light dates back to the time of Newton. Fraunhofer, however, devised a means of studying the solar spectrum without a prism. On plates of glass he ruled very fine parallel lines very close together, making the first grating. The beautiful iridescence of such substances as mother of pearl has been shown by the simple microscope to be due to a multitude of fine lines in the surface, the refracting edges of which disperse the prismatic colors like any true prism. Such a surface was the grating of Fraunhofer, and the great advantage of this instrument over the prism lay in the fact that the lower part of the spectrum where the red rays occur was very much spread out, whereas the simple prism dispersed the red end of the spectrum so little that examination of its characteristics was rendered difficult. Fraunhofer also experimented successfully with gratings made of very fine wire, 0.04 to 0.6 millimeters in thickness, or 0.002 to 0.03 inches in thickness. By the aid of similar gratings, John William Draper of New York not only confirmed the measurements of the light waves which Fraunhofer had made, but determined the temperature, 525 degrees centigrade, at which all solid and liquid substances become iridescent and glow with the red heat. He proved also that below this red heat invisible rays are emitted whose vibration lengths may be measured. Lewis Morris Rutherford, whose magnificent work in radioactivity has rendered him justly famous, produced other and better gratings made of thin sheets of metal, and Henry A. Rowland of Johns Hopkins University within very recent years ruled gratings so fine that they contained more than 100,000 lines to the inch, from 50 to 100 in the width of a fine human hair. Gratings have never been surpassed. With the aid of these wonderfully fine gratings, Rowland has prepared large photographic maps of the solar spectrum and prepared a system of standard wavelengths now universally adopted. The wavelength of every line in the solar spectrum has been measured through this means, and there are few of the common terrestrial elements which have not now been identified in the atmosphere of the Sun. The discovery of the invisible rays below the red of the solar spectrum dates back to Sir William Herschel, who in 1800 determined their existence by means of a thermometer. He noticed that the thermometer rose regularly when it was moved from the violet toward the red end of the spectrum, and it occurred to him to try the region beyond the extremes of the visible colors. To his delight, he found a regular series of radiations below the red. It is sometimes of great use in natural philosophy, the great astronomer observed, to doubt of things that are commonly taken for granted, especially as the means of resolving any doubt, when once it is entertained, are often within our reach. This discovery, says Thomas Young in his Lectures of 1807, must be allowed to be one of the greatest that has been made since the days of Newton. Yet the majority of physicists failed for more than half a century to see the importance of this discovery of Herschel. It was only a few years after the discovery by Herschel of infrared radiation from the Sun that Johann Wilhelm Ritter and Wollaston proved the existence of dark chemical rays in the ultraviolet region of the spectrum. Macedonio Melloni, the inventor, with Leopoldi Nobili of the thermopile, was the first to arrive at a thorough realization of the identity of radiant heat and light. Light, said he, is merely a series of calorific indications sensible to the organs of sight or vice versa. The radiations of obscure heat are veritable invisible radiations of light. He argued that where there is light of any sort, there must be some heat, and moonlight ought to show some heat effects. He experimented at first unsuccessfully in this direction, but finally, with a lens more than 3 feet in diameter, succeeded in getting feeble indications of heat from the rays of the moon. The thermopile which he used was a simple instrument based on the well-known principle that a cold wire is in general a better conductor of electricity than a warm wire. Hence, any simple galvanometer or other current measuring apparatus showed by a deflection of the needle when any part of the electric conductor was heated. The measurements of radiant heat made by Melloni in solids and liquids were paralleled by the investigations of Tyndall upon the diathermancy of gases. Tyndall possessed extraordinary powers of popularizing difficult scientific subjects. His first great lecture, delivered in 1853 in England, took his audience by storm. He came to America and delivered in 1872 and 1873 several lectures on light which were enthusiastically received. His famous Belfast address brought upon the brilliant Irishman the charge of infidelity, for he was as independent in thought, as outspoken in expression, and held ever to the principle that truth has nothing to fear from its enemies. Tyndall pointed out, as had Maloney before him, an error of wide prevalence concerning the influence of color and absorption. Benjamin Franklin records of himself that having placed patches of different colored cloth of the same weight upon snow, and allowed the sun to shine upon them, he found that they absorbed the solar rays to different degrees and sank to different depths in the snow. He concluded from this experiment that dark colors were the best absorbers and light colors the worst. For the visible rays of the sun, this conclusion is in general true, but the solar rays consist of radiations running far outside the visible spectrum, about 7 times the length of the solar spectrum having been detected in the infrared radiations, and perhaps twice as much as is visible in the invisible ultraviolet. The visible spectrum of white light has been shown by recent measurements to be only about 1/10 of the actual measurable solar spectrum. In the invisible region of the spectrum, effects are often observed which are the exact opposite of those seen in the prismatic spectrum. Tyndall proved this in a clever manner. He coated the bulb of a delicate mercury thermometer with the white powder alum, and the bulb of a second thermometer with powdered iodine. Exposing both bulbs at the same distance to the radiations from an ordinary gas jet, he found the alum-coated thermometer rose nearly twice as high as the other. Alum was a better absorber than iodine. The radiation, he remarked, from the clothes which cover the human body is not at all to the extent sometimes supposed dependent upon their color. The color of animals' fur is equally incompetent to influence radiation. Some of the first results of the invention of Langley's bolometer were to show that the maximum heat of the solar spectrum is in the orange, not in the infrared, as Herschel had supposed. It proved, moreover, that the white light from the sun is not the sum total of the solar radiations, that the sun's true color is blue, and only the orange veil of the terrestrial atmosphere works through its selective absorption on sunlight, letting through the red rays and absorbing the blue to produce the effect of white. Strictly speaking, we should say with Professor Langley that the atmosphere absorbs all the colors, but selectively taking out more orange than red, more green than orange, more blue than green. As there are really an infinite number of shades of colors in the spectrum, says Langley, it is merely for brevity that we now unite the more refrangible colors under the general word blue, and the others under the corresponding terms orange and red. Newton showed that white light is compounded of blue, red, and other colors. By turning a colored wheel rapidly, all blend into a grayish white. Arrange them so that there is too much blue, and the combined result is a very bluish white, that of the original sun ray. Alter the proportion of colors so as to virtually take out the excess of blue, and the result is colorless or white light. White, then, is not necessarily made by combining the 7 colors, or any number of them, unless they are there in just proportion, which is in effect what Newton himself says. And white, then, may be made out of such a bluish light as we have described, not by putting anything to it, but by taking away the excess which is there already. Langley and T.W. Very showed by studying the radiations of the firefly that it is possible to produce light without heat, other than that in the light itself, that this is actually effected now by nature's processes, that nature produces this cheapest light at about 1/400th part of the cost of the energy which is expended in the candle flame, and at but an insignificant fraction of the cost of the electric light. Langley showed also that the amount of energy necessary to produce the sense of color varies enormously with the color. The sensation of red, for example, requires that the energy of the waves which enter the eye shall be 100,000 times as great as the energy necessary to produce the impression of green. Far down below the visible red of the solar spectrum, the delicate filament of Langley's bolometer groped its way until a point was reached at which the solar radiations seemed to be suddenly cut off. From terrestrial sources, however, he obtained still further wavelengths, which exceeded in length 0.03 of a millimeter, or more than 0.001 of an inch. Rubens and Nichols, using a modified form of Crookes radiometer, found still longer wavelengths, equal to about 1/100th the length of the shortest Hertzian waves. Thus radiations of almost every length from the great electric oscillations of Hertz, several miles long, down to the ultraviolet rays less than 0.000009 of an inch, have been definitely measured. Enormous strides have been made in the measurement of all kinds of radiations, thanks to the invention of the Hertz receiver, the electric eye, as Sir W. Thomson calls it, a simple instrument, nothing but a bit of wire or a pair of bits of wire adjusted so that when immersed in strong electric radiations, they give minute sparks across a microscopic air gap. Thus, Sir Oliver Lodge. It was the theory of the great mathematician James Clerk Maxwell that light and electricity are fundamentally one, upon which Hertz conducted his studies, leading to the production of those wonderful waves which today, through the improvements of Marconi, convey messages 1,000 miles away through empty air. In a lecture delivered a few years before the close of the 19th century, Lodge said of such oscillations, "Light is an electromagnetic disturbance of the ether. Optics is a branch of electricity. Outstanding problems in optics are being rapidly solved now that we have the means of definitely exciting light with a full perception of what we are doing, and of the precise mode of its vibration. It remains to find out how to shorten down the waves, to hurry up the vibration until the light becomes visible. Nothing is wanted but quicker modes of vibrations. Smaller oscillators must be used, very much smaller, oscillators not much bigger than molecules. In all probability, one may almost say certainly, ordinary light is the result of electric oscillation in the molecules of hot bodies, or sometimes of bodies not hot, as in the phenomenon of phosphorescence. Anyone looking at a common glowworm must be struck with the fact that not by ordinary combustion, nor yet on the steam engine and dynamo principle is that easy light produced. So soon as we clearly recognize," he concludes, "that light is an electric vibration, so soon shall we begin to beat about for some mode of exciting and maintaining an electrical vibration of any required degree of rapidity. When this has been accomplished, the problem of lighting will have been solved." End of section 13.
Section 14 of The Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Emily Mercer. The Science, History of the Universe, Volume 3. Edited by Francis Rolt Wheeler. Physics, Chapter 8. Sound, Part 1. There is no more general instinct in man than love of the music of nature. Often, too, the light accents of almost inaudible sounds are more eloquent and persuasive than the louder vibrations heard in a world where every smallest particle of matter vibrates. The whole physical universe is but a fathomless ocean of vibrations, although only a few of these appear as audible sound. Yet in human history no physical sense has had such fatal influence as that of hearing. The vocal Memnon of Egypt, the oracles of Greece, the war trumpets of Rome, the vibrant harpstrings of Scandinavian skald, the shrill call of bagpipes, the booming tree drums of the South American Indians, the violin of Rouget de Lille, the triumphant crash of modern regimental band or mass symphony orchestra. Finally, the human voice. It needs but a glance at a few such examples to prove how surpassing is the influence of sounds that impinge upon the ear on the mind. It is said that Apollo was once wandering along the shore of the Mediterranean Sea and found there the shell of a dead turtle with a few strings of dried flesh stretched across it. He held it up and delighted himself with the musical sound which it made in the wind. He plucked the strings and found that they made a pleasing sound together. Such was the origin of the lyre. Pythagoras constructed on this model an instrument of a single string, the monochord, which was capable of producing notes of various pitch. The string was stretched above a board, and running over a bridge was attached to weights by means of which the tension on the string could be adjusted. Strange theories that the Greeks had as to the nature of sound. Not the least curious of these theories was that enunciated by Alcmaeon of Crotona, who wrote, "We hear with the ear because it contains a vacuum." Little as they knew of what is called today the science of sound, however, the Greeks carried the theory of music to a high degree of development. They were familiar with the diatonic scale of C and wrote massive bass melodies using natural notes, these melodies being classified as modes, according to the note upon which the melody ended. They had 6 such modes ending on every note of the scale except the 7th. The accompaniment was put in above the melody in a manner exactly reverse of that now generally in use. The so-called Ionian mode corresponded to the modern scale of C natural, the Mixolydian to that of G natural, the Aeolian to the scale of A minor. These same modes, adopted from Greek by St. Ambrose and added to by St. Gregory, became the basis of many of the grand melodies still extant in the ritual of the Catholic Church. The Greeks also recognized 3 genera, or varieties of modulation, the diatonic, the chromatic, and the enharmonic. The latter contained intervals similar to a semitone, the least difference of pitch to which modern ears are accustomed. The peripatetic school of philosophers held that the higher the pitch of a sound, the greater was its velocity. They also believed that the source of a sound determined the speed of its transmission, errors which were not disproved until early in the 17th century. Oracles played an important part in the history of Grecian development, as in fact in that of most ancient nations. The simple device of a speaking tube made it possible to produce those mysterious voices, whose supernatural revelations so swayed the imagination of an unsophisticated people. Such were the cryptic and potent utterances of the famous Greek at Oracle Delphi. To the modern mind, accustomed to wonder at nothing, to explain everything, the faith in men in the oracular utterances of antiquity seems as barbarous, childish. Yet the roar of trains and machinery, the whistles, bells, and rattling of wheels of commerce cannot drown the quiet voice of the savant, the man who knows. The oracle still speaks, but speaks today from the mysterious retirement of the laboratory with an authority as absolute as that which bid the Athenians defend their city with wooden walls. It is apparent that the multitude of sounds which reach the ear must be conveyed to it by some material medium. In most cases, this medium is the air. Indeed, the striking fact has long since been pointed out that but for this atmospheric ocean, the world would be plunged for us in perpetual silence. The bell jar experiment of Francis Hauksbee, made in the 17th century, proved that no sound is audible in a vacuum. The ringing of a bell became rapidly fainter when the air was exhausted from the bell jar under which it was placed. The fact that air is not the only conductor of sound, nor the best, is well known. Tapping a table, the sound is heard much more distinctly when the ear is placed close to the wood. The Indian places his ear near the ground to note the sound of approaching footsteps. An oncoming train is heard through the rails long before the sound of it reaches through the air. The detonation of a distant explosion comes with a double shock, the sound traveling faster through the earth than through the air. In addition, then, the more dense the medium is, the better conductor does it become of sound waves. Liquids transmit the vibrations of sound better than gases. Stones clapped together underwater produce a sharp, stunning effect upon the ear placed under water to hear them. The bell signals installed on the American coast give practical evidence of the superior transmitting power of water over air. The velocity of sound in air was investigated in the 16th century by Marin Mersenne, noting the difference in time between flash and the report of firearms at known distances. He got 1,380 feet per second as the speed of propagation of sound waves. This result was far from accurate. Pierre Gassendi, making similar experiments, used guns large and small and disproved the Aristotelian theory that the velocity of sound was dependent upon source and pitch. To anyone, indeed in modern days, this idea of the peripatetic school must appear absurd. For the pitch and source of sounds from a modern orchestra are as various as musical genius can make them, yet when played together the sounds of all reach the ear at the same moment. That the source of sound does not affect speed of its transmission is not, however, universally true. Captain Parry, on his Arctic expedition, found that violently loud sounds would travel faster than softer ones. During artillery practice, it was shown that by persons at distance from the guns, the report of the latter was heard before the command of the officer to fire. In a series of experiments upon the velocity of sound in rocks, Mallet showed, with a charge of 2,000 pounds of gunpowder, the average velocity of the sound was a blast 967 feet per second, while a charge of 12,000 pounds produced a speed of transmission of 1,210 per second. Through iron, the speed of sound has been shown to be still faster. M. Byatt, experimenting with an iron tube 3,120 feet long, found the speed of sound through this tube to be 9 or 10 times as fast as in air. It is now generally conceded that the speed of sound in iron is actually about 5 times as fast as in air, and through water about 4 times as fast. The great law of inverse squares, which has been shown to be so general in physics, applies also to sound. If 4 bells of the same kind are placed at a distance of 20 yards from the ear and another at a distance of 10 yards, the single bell produces a sound as loud as that of the 4. How far a sound is audible depends on its loudness. The report of a volcano at St. Vincent was heard at Demerara 300 miles away, and the cannons of the Battle of Waterloo are said to have been audible at Dover. The study of sound and music, the classification of tones and their combination, reached a high point of development long before any complete analysis had been made of the cause of sound and the manner of its transmission. About the end of the 17th century, Joseph Sauveur, a poor adventurer who found his way on foot to Paris seeking his fortune, became professor of mathematics at Collège Royal. He published important papers on the discovery of overtones in strings, using paper writers to locate the points of greatest and least motion when the strings were set in vibration. He had observed and explained the phenomenon of sympathetic vibration. From the beats produced by organ pipes of nearly equal length, he determined the vibration rates of notes given forth by each. 2 pipes were tuned in the ratio of 24 divided by 25. When air was blown into these, 4 beats per second were observed, from which Sauveur concluded that the higher-pitched pipe was producing 100 vibrations per second. The experiments of William Noble and Thomas Pigott at Oxford had proved the vibration of a string is greatest at the center, and it may also be made to vibrate in halves, thirds, fourths, fifths, etc. The strings of a harp or piano, for example, vibrate chiefly as a whole, that is, throughout their entire length. The harder the string is plucked or struck, the louder is the sound, and the more ample is the motion of the string. Thus, amplitude of vibration was seen to be a determining factor in the loudness of a sound. Not only nearness and amplitude of vibration, but echo as well may increase the intensity of a sound. Speaking tubes, megaphones, and such devices depending on this principle were in use long before the theory of sound was generally understood. The effect here is evidently one of reinforcement by echo, which in smooth tubes is so great that M. Byatt observed that a conversation could be carried on in a low tone through a small tube 1,040 yards long. For very long distances, however, it is evident that the speaking tube is not a practical device, as it would require 8 minutes for sound to travel from one town to another 100 miles away, less than 1/10 of the distance equally and instantly bridged today by wireless telegraph. The father of acoustics introduced about the end of the 18th century a new chapter in the study of sound. Ernst Florenz Friedrich Chladni, educated for the law, proved himself a much better scientist than lawyer. He experimented with vibrating plates covered with sand. The collection of the sand at nodes, or points of least vibration, formed the famous figures of Chladni. These were exhibited before Napoleon, and the conqueror of Europe presented him with 6,000 francs to enable him to translate into French his acoustic. Clundy invented a torsional pendulum in which the motive force of gravity was replaced by the molecular resistance of a rod to the effect of twisting. He made many calculations of the absolute rate of vibration of sounding bodies and determined the velocity of sounds in other gases than air by filling organ pipes with a gas, noting the resulting pitch. Felix Savart, the greatest master of his time in the theory of sound, invented a simple but effective instrument to show that the vibration rate of a body is the sole factor of the pitch in the note which it produces. A toothed wheel was made to rotate rapidly against the edge of a card. By increasing or decreasing the speed of rotation, the pitch of the note produced could be raised or lowered at will. A dial indicated the number of shocks per second made by the teeth of the wheel striking the card. Caynard Latour invented about the same time an instrument often heard today in connection with steam whistles, the siren, so called because it could produce sounds audible in water as well as in air. A current of air blown through holes in a swiftly revolving disc produced notes at which could be regulated to give any desired pitch. This apparatus of Latour was used by Savart with certain improvements to determine the limits of audible sounds. He found that he could hear tones of bodies vibrating at a rate of 48,000 per second. The lower limit of audible vibration he placed at 16 or 14 per second. With the same velocity, the siren gives the same sound in water as in air and all gases. Thus, the number of vibrations per second, irrespective of the material of the vibrating body, was proved to be the sole factor in determining pitch. It is interesting to note that the siren has been applied to find the rapidity of motion in the buzzing wings of insects. The tiny gauze pinions of the great gnats have thus been found to vibrate 15,000 times in a second. About the middle of the last century was invented an instrument so similar to the human ear that it deserves some attention. E. Leon Scott produced an apparatus which he called the phonautograph, so beautifully constructed as to register not only the vibrations produced by solid bodies, but also those produced by wind instruments, by the voice in singing, and even such noises as that of thunder or the report of a gun. A small cask of plaster of Paris, perhaps 1.5 feet long, was closed at one end, but for a small circular space over which was fitted a flexible membrane. Plaster of Paris was selected on account of its absence of elasticity and its very slight susceptibility to vibration. A stylus or blunt needle, in contact with the membrane, recorded the vibrations of the latter upon a revolving cylinder. A movable piece, called the subdivider, enables the experimenter to adjust at will the arrangement of the lines of greatest and least vibration. Comparing the ellipsoid cask with the auditory canal, he stretched the membrane with the tympanum, or drum of the ear, and subdivider with the chain of little bones which touch the tympanum. The likeness of this instrument, the organ of hearing, becomes singularly apparent. Before the researches of Savart, it was generally assumed that sounds above 18,000 per second and below 32 per second were inaudible to human ears. M. Despretz, investigating the same subject, disputed Savart's results, maintaining that the higher and lower limits of audible sound were respectively 73,700 vibrations and 32 vibrations per second. It is probable that the ears of even trained experts will vary greatly in their sensibility to sounds of extreme pitch. The intensity of a sound will also evidently make it audible when another less intense sound of the same pitch cannot be heard at all. The question of quality of sounds was first clearly explained by the great Helmholtz. His Lehre von dem Tonempfindungen has gone through many German and English editions. This wonderful investigator, mathematician, and physicist showed that musical tones were due to regularity of vibration, discordant tones to irregularity. Musical tones he distinguished by their intensity, pitch, and quality. The quality of a sound, he found, depended upon the number of upper partials, or overtones, present in the vibration of any body. The electrician Georges S. Ohm was the first to point out that there is only one form of vibration which will give rise to no overtones, but consists only of fundamental note. This was the vibration peculiar to the pendulum and tuning fork. Helmholtz's experiments showed analytically the composition of vowel qualities, how the infinite subtleties of inflection in the human voice are due not so much to the loudness or softness of the instrument as to the number and position of these upper tones present with and surrounding with the fundamental. If only the unevenly numbered partials, says he, are present, as in narrow, stopped organ pipes, piano strings struck in their middle points, and clarinets. The quality of the tone is hollow, and when a large number of such upper partials are present, nasal. When the prime tone predominates, the quality of tone is rich, but when the prime tone is not sufficiently superior in strength to the upper partial, the quality of tone is poor. Helmholtz designed a series of glass globes, resonators, which he made such size as to correspond with the vibration numbers of the upper partials of a given fundamental tone. When the fundamental tone was sounded, he held each one of these resonators to his ear, and if that particular overtone were present, it would at once be reinforced and exposed by the resonator. Thus he proved beyond question the fact that it is the overtones of any given note which lends to its peculiar character, tone color, or timbre. Rudolf Konig, the eminent instrument maker of Paris, constructed a series of resonators which were an improvement upon the designs of Helmholtz. He made his resonators cylindrical in form, having over one end a close-fitting cap, by means of which the cylinder could be drawn out and tuned to a nicety. Then he conceived the brilliant idea of arranging these resonators on a frame connected with a mammometric mirror, whereby the presence of each and every overtone could be instantly detected by the dentations of the flame. But Helmholtz was not content with the analysis of tones according to their quality. He verified his results by the synthesis of the same tones of their constituents. By means of a series of electromagnets, he succeeded in making all possible combinations of overtones and producing notes of every quality. Professor Ganon's Éléments de Physique thus summarizes the facts which the inestimably valuable researches of Helmholtz have contributed to the study of tone color. 1. Simple tones, as those produced by a tuning fork with a resonance box and by a wide-covered pipes, are soft and agreeable without any roughness, but weak, and in the deeper notes, dull. 2. Musical sounds accompanied by a series of harmonics, say up to the sixth in moderate strength, are full and musical. In comparison with the simple notes, they are grander, richer, and more sonorous. Such are the sounds of open organ pipes, of the pianoforte, etc. 3. If only the uneven harmonics are present, as in the case of narrow-covered pipes, of pianoforte strings struck in the middle, clarinets, etc., the sound becomes indistinct, and when a greater number of harmonics are audible, the sound acquires a nasal character. 4. If the harmonics beyond the sixth and seventh are very distinct, the sound becomes sharp and rough. If less strong, the harmonics are not prejudicial to the musical usefulness of the notes. On the contrary, they are useful as impairing character and expression to the music. Of this kind are most stringed instruments and most pipes furnished with tongues, etc. Sounds in which the harmonics are particularly strong acquire thereby a peculiarly penetrating character, such as those yielded by brass instruments. M. Jules Lissajous designed a method of tracing by means of a stylus the vibration of two tuning forks, known as Lissajous figures. Nathaniel Bowditch of Salem, Massachusetts, had also previously to Lissajous' experiments succeeded in producing the same figures. End of section 14. Recording by Emily Mercer. Section 15 of The Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Emily Mercer. The Science, History of the Universe, Volume 3. Edited by Francis Rolt Wheeler. Physics, Chapter 8. Sound, Part 2. From the evidence of the researches of Helmholtz, it is evident that a pure tone is almost never heard. The notes of a violin, or of a beautiful voice, or of a piano sound, it is true, like simple tones. They are not simple, in fact. The most pleasing tones which can be heard are, as a rule, very complex. A note struck on the piano sounds forth simultaneously a number of other notes. These may not first appear, but if the note struck is held down for a few minutes, even the untrained ear will infallibly distinguish other notes of higher pitch, which seem to take shape and stand forth separately from the sounding interior of the instrument. These auxiliary tones are frequently classed under the general head of harmonics. Helmholtz called them upper partials. Tyndall gave them the name of overtones. The strings of a violin or cello may likewise be made to produce different notes by setting them into vibration with the bow in the usual way and merely touching the vibrating string at various points. Violin soloists became phenomenally skilled in the use of these harmonics, which can be produced with equal readiness on the stopped or on the open strings. The same effects may be observed in a piano if the string happens to be accessible. From any string under tension, harmonic effects may be obtained. Let the A string of a cello, for example, be bowed and at the same time lightly touched in the middle by a finger. A note will at once appear which is the octave above the open string, and the string will be seen to be vibrating in two sections in place of one. A paper writer will remain quiet when placed in the middle of the string, but if the latter is made to vibrate throughout its whole length, the writer will be violently thrown off. Again, the string may be divided by a touch and made to vibrate in thirds, fourths, or fifths. Dividing the string in thirds is clearly evident till multiplying its vibration number by 3. Each of these divisions will therefore give out a note whose vibrations are 3 times as frequent as those of the fundamental. In musical terms, this is said to be an octave and a fifth above the open string. If the vibration number of the A string be taken at 213 vibrations per second, the octave and fifth, E, will then vibrate 3 times as frequently, giving 639 vibrations per second. These figures, while not quite accurate, are close enough to illustrate by a rough computation how the values of harmonics were determined. Dividing the same string of 213 vibrations per second into 4 parts, a note is obtained 2 octaves above the open string, A, and the vibration number of this note will, in the same manner, be 4 times that of the fundamental, giving therefore the number 852. The division of the string into fifths produces a note which has 5 times the vibration frequency of the fundamental. This note will prove to be C sharp, 2 octaves and a third above the original note. A little careful experimentation will show that several higher harmonics may readily be produced by this one string. The harmonics produced by sounding a note on the piano and listening for its overtones will usually appear the wrong order. The higher harmonics, on account of their more dissonant relation with the fundamental, coming to the fore first. The natural series of overtones follows in whole tones after the 7th, but none of these are exactly in tune, and after the G, A, B, C sharp have been passed, a partial tone appears that cannot be located by the notation in common use today. In the pitch generally recognized by physicists, C has a vibration frequency of 256 per second. International standard pitch, so called, is made slightly higher than this in the endeavor to lend a more brilliant quality to the instrument. The pitch of a given note, therefore, is not always constant. A brief consideration, however, will show that not only is this the case, but that the tone relations of a note are not constant, and this same note in different natural scales must have a different vibration rate. The fact that the natural scale in use today is not natural but artificial, the diatonic scale is not diatonic. For purposes of modulation, it became necessary to temper the natural series of notes which would occur as overtones from a given fundamental. Thus, the perfect fifth, G, above note C is actually about 1/50th of a semitone flat, and the F next below it is made sharp to a still greater extent, while the other notes of the scale are tempered more than these. A perfectly tuned piano has not a single note, excepting the octaves, in tune. The complex nature of the apparently simple major scale may easily be apparent. The scale from C to C has in it 8 natural notes, white, and 5 accidentals, black. Excluding the octave, this makes the 12 notes. Theoretically, the major scale was originally derived from the first overtones of a given fundamental. All these natural notes of the scale, except the 7th, are found in the overtones of the note C, but the interval from the first to the second note of the scale is not in the same interval from the second to the third. The introduction of the minor melodies and a minor scale made the problem still more difficult, for the ratio between E flat in the perfect scale and C is not at all the ratio between D sharp in the perfect scale and the same note C. Consequently, D sharp and E flat must both be altered to the same intermediate note, since in an instrument, like the piano, of fixed pitch, the same key must be struck to represent both these notes. The problem was finally solved by dividing the notes from C to its octave above C into 12 equal steps or intervals, and by this means producing a tempered scale, of which the notes, black or white, could be played in any key. For this instrument, so tuned, Johann Sebastian Bach, the greatest of all great composers, wrote his Das wohltemperierte Klavier, showing that these fixed and tempered notes music could be played in any key whatsoever. It is related of the great Handel that he could not bear to hear music played in the tempered scale, and had constructed for himself an organ provided with keys to produce every one of the notes theoretically necessary for a perfect scale. This would really require a keyboard containing about 20 notes to the octave, and more than this if such accidentals as double sharps and flats could be accurately represented. A glance at the accompanying table will show how each note of the tempered scale compares with its true value in the natural scale. Natural, C, 24. Tempered, 24. Natural, C sharp, D flat. Tempered, 25.43. Natural, D, 27. Tempered, 26.94. D sharp, E flat. Tempered, 28.55. Natural, E, 30. Tempered, 30.25. Natural, F, 32. Tempered, 32.05. Natural, F sharp, D flat. Tempered, 33.96. Natural, G, 36. Tempered, 35.98. Natural, G sharp, A flat. Tempered, 38.12. Natural, A, 40. Tempered, 40.38. Natural, A sharp, B flat. Tempered, 42.80. Natural, B, 45. Tempered, 45.33. Natural, C, 48. Tempered, 48. It is a problem for the musical physicist of the future to devise a keyboard adapted to play in perfect tune the perfect scale in every key. Musical instruments are among the earliest recorded human inventions. In the Hebrew scriptures, mention is made of one Jubal, who became the father of all such as Handel, the harp, and the organ. The Hebrews had many musical instruments, harps, trumpets, and flutes of various styles. The Egyptian inscriptions likewise portray types of all these instruments. They developed also an organ, a set of panpipes with bellows. From the Phoenicians, the Greeks are said to have imitated the cithara, zither, or lyre. The sabica of the Chaldeans was the precursor of the modern harp. The psalterin of the clavichord, from which evolved the modern piano. The bagpipes were known from the very beginning of history in Syria, Phoenicia, and Egypt. Such early instruments as these were designed rather to accompany singing and religious ritual than for solo performances. The use of instruments unaccompanied by the human voice is an essentially modern idea. The infinite combinations of tone heard in a modern orchestra are the product of four main classes of instruments. 1. The strings. 2. The woodwind instruments. 3. The brass instruments. 4. The percussion instruments. More than half of a well-balanced orchestra today is made up of stringed instruments, the violins, the violas, cellos, and bass viols. As the latter three are identical in general construction with the violin, the difference being mainly one of size, a word concerning the latter will of course apply to all in this group. Vibration of the strings alone of a violin, made by drawing a bow across them, would have so little resonant value that the sound would be almost inaudible and the instrument about as serviceable as an orchestra of a Jew's harp. The tone must therefore be reinforced. And this is done by the body of the violin, every part of which is forced into vibration when the strings vibrate. A just proportion of the construction of the violin box is the secret which the great Cremona violin makers, the Guarneri and Stradivari, discovered. The wood must not be too thick, for the vibration then will be dull and smothered, nor too thin, for then the tone of the instrument lacks body, richness, mellowness. The material must be perfectly seasoned, so that no subsequent contraction of the fiber may strain and destroy the perfect proportion on the parts of the instrument. The adjustment of the bass bar beneath the heaviest string and supporting 1 foot of the bridge, of the sound post which supports the other foot of the bridge, the adjustment, carving out, and proportioning of the bridge itself, the length of neck and size of head, the varnish which fills and protects the surface of the wood, the shape of the body, the position, size, and shape of the sound holes. All these and other conditions affect the construction of a perfect instrument. By bowing nearer to or farther from the bridge, the note is made either bright or soft and mellow. If the vibration is excited near the bridge, a large number of the higher overtones are brought out. If further away, the fundamental and primary overtones assume greater prominence, for the larger the segments in which the principal vibrations occur, the less will the tone be affected by the higher partials. If the string is bowed too far from the bridge, it loses its sonorous quality and becomes feeble in tone. The violin, therefore, is bowed at points which vary from 1/8 to 1/12 of the string length from the bridge, and the instrument is thus able to produce more varieties of tone color than are found in any other one instrument. In the others of this class, the quality of the tone grows gradually more somber as the instrument increases in size and weight, and the greater size of string necessitates bowing further from the bridge. Even the bass viol, or violone, however, may be used occasionally as a solo instrument, giving a magnificently rich, ponderous tone. The production of sound in the brass instruments depends upon the use of overtones. The fundamental pedal notes of these instruments are seldom heard. In the bugle, the simplest of the brasses, the second, third, fourth, and fifth overtones are alone used. For example, a C bugle will produce among its natural overtones the notes G, C, E, G. And with these four notes, by aid of change of rhythm, all the military signals may be produced. A trombone, if in this key, would add to these notes, the octave C. Here, however, a new principle is introduced. By means of the slide, the length of the trombone tube may be increased. Suppose the slide to be pushed out about 1.5 inches. It is clear that the pitch of the whole instrument will be lowered. It will give exactly the same series of overtones, but each will be found about a semitone below its original pitch, thus producing notes F sharp, B, D sharp, F sharp. It should be noted that a trombone is exactly an octave lower than a bugle, cornet, or trumpet in the same key. Pushing the slide out another 1.5 inches again lengthens the tube and again lowers the instrument, a semitone, giving the series F, B flat, D, F. This is actually the key in which the orchestral trombone lies with the slide closed. By repeating this process of lowering the slide, all the semitones in the scale may be produced as far as the compass of the instrument extends. The pedal note of the trombone may similarly be lowered by means of the slide. In all of the brass instruments other than the slide trombone, the overtones are lowered by means of finger valves which introduce different lengths of pipe into the vibrating tube. The trombone is not infrequently, especially in brass hands, provided with such valves in lieu of the slide, and the physical principle of the instrument then becomes identical to that of the French horn, cornet, trumpet, and tuba. The French horn produces a tone singularly soft among the brasses, sounding often more like some wood and wind instruments. The quality of tone of this instrument has been explained on the basis of the conical bore of the tube and the immense bell at the end of it. The sound is softened and mellowed by the oblique reinforcement of echo from the walls of the tube. The trumpet, on the contrary, by far the most brilliant instrument in existence, is said to owe its superiority in this regard to the cylindrical bore and small bell of the tube. The vibrations are not lost, as in the spreading walls of the French horn, cornet, etc. The woodwind instruments are of 3 types. The flute and piccolo, or octave flute, are made to sound by the breath of the player blown across a hole in the instrument and striking the opposite edge. Different notes are produced by the keys, which open holes in the side of the flute, thus causing the air within to vibrate in various sections at the will of the player. The oboe, English horn, or tenorune, and bassoon have 2 thin reeds in the mouthpiece, which set into vibration the column of air within the instrument. The extremely reedy tone of the instrument has caused it to be used a great deal for pastoral effects in what is called descriptive music. This penetrating, soft, but reedy quality, when brought down into the bass register, as in the bassoon, has an effect sometimes ludicrous, sometimes terrifying, always peculiarly characteristic. The flutes of the Egyptians are believed by some authorities to have been in reality of the oboe type. It is probable that they frequently used reeds in the end of the pipes, and that the latter would be classed today as either oboes or clarinets. The clarinet principle is not essentially different from that of the oboe, except that it has one reed instead of two. The instrument is made in several pitches. A high clarinet in E-flat is much favored in band music, but appears seldom in orchestra. There are also a bass and an alto clarinet, which are recognized by composers, these instruments being identical in principle with the A and B-flat clarinets of an orchestra. The quality of these instruments partakes of both soft and floating notes of the flute and highly nasal character of the oboe. Although there is probably no instrument so primitive as the drum, yet the kettle drums of the modern orchestra are by no means primitive instruments. Their value is chiefly in the tremendous energy which they add to rhythmic effects, but they can also be tuned through a surprisingly wide range of notes, although of low pitch and dull quality of tone, producing no definite musical tone color. The copper hemisphere above which the sheepskin head is stretched acts as a perfect resonator, and the tone of the drum, partly on the account of this large reflecting surface, has an amazing carrying power. Of other percussion instruments, such as the cymbals, snare drum, tambourine, xylophone, etc., which have come down with little or no change from the earliest times, only passing mention need be made. A familiar but beautiful instrument, different in principle from any of these heretofore mentioned, is the Aeolian harp. In this the strings are set in motion by the varying currents of wind upon them. Since no resonator reinforces the tone of the strings, the quality of the sound is exceedingly soft and ethereal, although distinct enough in point of pitch. Sound, therefore, like light and heat, may be considered in a double aspect, that of the physicist and of the artist or musician. The laws of physics cannot be considered merely as cold abstractions, for the reason that they are so intimately related to the aesthetic interests of life and the advancement of human well-being. The better understanding of the properties of matter has led to this era of mechanical knowledge, and the comprehension of the principles of heat has enabled man to obviate much climatic inclemency. The length of available time for labor and pleasure has been increased by artificial lighting, and speech is dependent upon the hearing of the sound. And yet even the vast domain of these great subjects is scarcely known, but half explored, and the 20th century awaits to welcome the Newton of the future. End of section 15. Recording by Emily Mercer.
Section 16 of the Science, History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 1, The Nature of Electricity. So rapidly have the applications of electricity to the wants of industry followed one another during the past 30 years that it may seem as though the whole science had been practically developed in that time, and yet the real foundation work, which make the most innumerable electrical contrivances of today possible, was mainly laid long before that period. It was Gilbert, Franklin, Volta, Galvani, Davy, Arago, Faraday, Maxwell, and many others, who have enabled the modern experts to put much of the science on a mathematical basis, and who made long strides toward that final goal which is still so far away, the answer to the question, what is electricity? Many are the philosophers who are still devoting their lives to it, and occasionally some fact is discovered which disarranges many existing ideas and leads to new and unexplored fields. The new theories which have been advanced, however, have striven rather to elucidate some unexplained points of the old theories than to disprove them. Thales in 600 BC, who discovered the attraction of amber for light bodies, said that amber had a soul. Gilbert in 1600 AD is accredited with the following hypothesis. Friction, because it heats a body, causes it to emit rays of a subtle, unctuous material, which is cooled again, on coming into contact with the air, loses its expansive force, and draws itself together again, bringing back such light bodies as come in the way of the electrified body. According to Hauksbee, the emanations of matter, which start from an electrified body, spread in the form of rays or physical lines, which possess a kind of continuity in themselves, so that those parts of each ray or line which reach out furthest into space receive the impulse from those parts which are nearest to the body. The 18th century brought out two theories, which for a time seemed to explain most of the phenomena then observed. One was the two-fluid theory of Simmer, and the other the single-fluid theory of Franklin. Both these theories assumed electricity to be a fluid. Franklin assumes the existence of one electrical substance or fluid, which attracts the particles of ordinary matter, but repels itself. In the ordinary state, bodies are charged with a normal quantity of this electrical substance. If this charge be either increased or decreased, the body becomes electrified. If it be increased, the body is charged with a plus or positive charge. If the body has a less quantity of electricity than in its normal state, it is said to be charged with a minus or negative charge. The two-fluid theory thought out by Simmer supposes that instead of there being one fluid, there are two fluids having opposite properties to each other. The molecules of each fluid repel one another, but attract those of the opposite kind of fluid. Bodies in their normal condition, or when unelectrified, contain equal quantities of both fluids held together by their mutual attraction, so neutralizing each other. By friction or by induction, the two fluids may be separated. The positive fluid passes to one of the bodies and accumulates on its surface, thus leaving an excess of negative electricity on the other. These two theories were convenient to use in explaining the action of frictional and influence machines, the electrophorus, the condenser, and many other forms of electrostatic apparatus. Indeed, these theories are still applied to a certain extent, as affording a convenient means of expressing these electrostatic actions. They contain a large element of truth, and the later theory of Maxwell and the electron theory are elaborations of them. Franklin's opinion on the nature of electricity may best be stated in his own words, and the following is an extract from his paper entitled Opinions and Conjectures Concerning the Properties and Effects of Electrical Matter Arising from Experiments and Observations Made at Philadelphia, 1749. 1. The electrical matter consists of particles extremely subtle, since it can permeate common matter, even the densest metals, with such ease and freedom as not to receive any perceptible resistance. 2. If anyone should doubt whether the electrical matter passes through the substance of bodies, or only over and along their surfaces, a shock from an electrified large glass jar taken through his own body will probably convince him. 3. Electrical matter differs from common matter in this, that the parts of the latter mutually attract. Those of the former mutually repel each other. Hence the appearing divergency in a stream of electrified effluvia. 4. But though the particles of electrical matter do repel each other, they are strongly attracted by all other matter. 5. From these three things, the extreme subtlety of the electrical matter, the mutual repulsion of its parts, and the strong attraction between them and other matter, arise this effect, that when a quantity of electrical matter is applied to a mass of common matter, of any bigness or length, within our observation, which hath not already got its quantity, it is immediately and equally diffused through the whole. 6. The common matter is a kind of sponge to the electrical fluid, and as a sponge would receive no water if the parts of water were not smaller than the pores of the sponge, and even then but slowly, if there were not a mutual attraction between those parts and the parts of the sponge, and would imbibe it still faster if the mutual attraction among the parts of the water did not impede, some force being required to separate them, and fastest if, instead of attraction, there were a mutual repulsion among those parts, which would act in conjunction with the attraction of the sponge. So is the case between electrical and common matter. 7. But in the common matter, there is generally as much of the electrical as it will contain within its substance. If more is added, it lies without upon the surface, and forms what we call an electrical atmosphere, and the body is said to be electrified. 8. 'Tis supposed that all kinds of common matter do not attract and retain the electrical with equal strength and force, for reasons to be given hereafter, and that those called electrics per se, as glass, etc., attract and retain it strongest and contain the greatest quantity. 9. We know that the electrical fluid is in common matter because we can pump it out by the globe or tube. We know that common matter has near as much as it can contain, because when we add a little more to any portion of it, the additional quantity does not enter but forms an electrical atmosphere. And we know that common matter has not, generally, more than it can contain. Otherwise, all loose portions of it will repel each other, as they constantly do when they have electric atmospheres. 15. The form of electrical atmosphere is that of the body it surrounds. Such are the essential parts of Franklin's primitive theory, propounded for the purpose of giving a consistent account of the phenomena of electric attraction and repulsion, so far as they were known in his time. It is curious to observe how some of his ideas were quite in keeping with the latest theory, the electron theory, described later. Various theories are propounded from time to time for a long time after the enunciation of the single and two fluid theories, but none served better as a working basis. In the latter part of the 19th century, however, a new theory dealing with electricity as obeying the laws of mechanics was formulated by Clerk Maxwell, the great English physicist. Maxwell's ideas were founded on the observations made by Faraday, who discovered that the nature of the insulating material, or dielectric, between the plates of a condenser had a great deal to do with the quantity of electricity which would flow into it under the influence of a given electromotive force. This fact led Maxwell to believe that the dielectric was the real seat of the charge, that the conductor acted merely to distribute the charge over the different portions of the dielectric in contact with it. When a flow of current takes place along a wire, it is due to the differences existing in the dielectric about the wire. The following extract from Maxwell's Theory and Hertzian Oscillations by H. Poincaré, translated by Frederick K. Vreeland, may serve to give some idea of the action in and about an electric current. If we undertake to compress a spring, he says, we encounter an opposing force, which increases as the spring yields to the pressure. If now we can exert only a limited pressure, a moment will arrive when we can no longer overcome the reacting force. The movement will cease, and equilibrium will be established. Finally, when the pressure is removed, the spring will regain its original form, giving back all the energy that was expended in compressing it. Suppose, on the other hand, that we wish to move a body immersed in water. Here again we encounter a reaction, which depends upon the velocity, but which, if the velocity remain constant, does not go on increasing as the body yields to the pressure. The motion will thus continue as long as the motive force acts, and equilibrium will never be established. Finally, when the force is removed, the body does not tend to return to the starting point, and the energy expended in removing it cannot be restored. It has been completely transformed into heat through the viscosity of the water. The contrast is manifest, and it is important to distinguish between the elastic reaction and viscous reaction. Now the dielectrics behave toward the motion of electricity as elastic solids do toward the motion of matter, while the conductors behave like viscous liquids. Hence there are two kinds of currents: the displacement currents of Maxwell, which traverse the dielectrics, and the ordinary conduction currents, which flow in conductors. The former, having to overcome a sort of elastic reaction, must be of short duration, for this reaction increases as long as the current continues to flow, and equilibrium must soon be established. Conduction currents, on the other hand, must overcome a sort of viscous resistance, and hence may continue as long as the electromotive force which produces them. To take a hydraulic analogy, suppose that we have a closed vessel containing water under pressure. If we put this vessel in communication with a vertical pipe, the water will rise in it, but the flow will cease when the hydrostatic equilibrium is established. If the pipe be large, there will be no appreciable friction nor loss of head, and the water thus raised may be used to do work. We have here an illustration of displacement currents. If, on the other hand, the water be allowed to run out through a horizontal pipe, the flow will continue as long as there is water in the reservoir. But if the pipe be small, there will be a considerable loss of energy, and heat will be produced by the friction. This illustrates the action of conduction currents. Although it is impossible and unnecessary to try to imagine all the details of the mechanism, we may say that all takes place as if the displacement currents had the effect of compressing a multitude of minute springs. When the currents cease, electrostatic equilibrium is established, and the tension of the spring depends upon the intensity of the electrostatic field. The energy accumulated in these springs, that is, the electrostatic energy of the field, may be restored whenever they are allowed to unbend, and it is thus that mechanical work is produced when charged conductors are allowed to obey their electrostatic attractions. These attractions are thus due to the pressure exerted on the conductors by the compressed springs. Finally, to pursue the analogy to the end, a disruptive discharge may be attributed to the breaking of some springs which are unable to stand the strain. On the other hand, the energy expended in producing conduction currents is lost and converted into heat, like the work done in overcoming friction or the viscosity of fluids. This is why a conductor is heated by the passage of a current. From Maxwell's point of view, none but closed currents exist. To the early electricians, this was not the case. They considered as closed the current which circulates in a wire joining the two terminals of a battery. But if, instead of joining these terminals directly, they were connected respectively to the two plates of a condenser, the momentary current which flowed while the condenser was being charged was considered as unclosed. It flowed, they said, from one plate to the other through the wire connected to the battery and stopped at the surfaces of the plates. Maxwell, on the contrary, considers that the current continues in the form of a displacement current across the insulating layer which separates the plates and is thus completely closed. The elastic reaction which the current encounters in traversing the dielectric explains the short duration. Currents may manifest themselves in three ways: by their heating effects, by their action on magnets and other currents, by the induced currents which they generate. We have seen above why conduction currents produce heat and displacement currents do not. Yet, according to Maxwell's hypothesis, the currents which he imagines should, like ordinary currents, produce electromagnetic, electrodynamic, and inductive effects. Why could these effects not be observed? Because a displacement current, however feeble, cannot continue long in one direction, for the tension of our hypothetical springs, continually increasing, will soon check it. Thus we cannot have in a dielectric either a continuous current of long duration or a sensible alternating current of long period, but the effects should be considerable if the alterations are very rapid. And here we have, according to Maxwell, the origin of light. A light wave is a series of alternating currents flowing in a dielectric, in the air, or in interplanetary space, changing their direction 1 quadrillion times in a second. The enormous inductive effect of these rapid alternations produces other currents in the neighboring portions of the dielectric, and thus the light waves are propagated from place to place. The velocity of propagation may be known analytically to be equal to the ratio of the units, that is, to the velocity of light. These alternating currents are a kind of electrical vibration, but are they longitudinal like those of sound, or transverse like those of Fresnel's ether? In the case of sound, the air undergoes alternate condensations and rarefactions, but the ether of Fresnel acts as if it were composed of incompressible layers capable only of sliding upon each other. If the currents flowed in unclosed currents, the electricity would necessarily accumulate at one end or the other of the circuits, and we should have a condition analogous to the condensations and rarefactions of air. The vibrations would be longitudinal. But as Maxwell admits only closed currents, those accumulations are impossible, and the electricity must behave like the incompressible ether of Fresnel. Its vibrations must be transverse. Thus we reach all the conclusions of the wave theory of light. This, however, was not enough to enable the physicists, who were attracted rather than convinced, to accept absolutely Maxwell's ideas. All that could be said in their favor was that they did not conflict with any known facts, and that it were indeed a pity if they were not true. The experimental confirmation was lacking and remained so for 25 years. It was necessary to find, between the old theory and that of Maxwell, a discrepancy not too minute for our crude methods of observation. There was only one such from which an experimentum crucis could be derived. To do this was the work of Hertz. Maxwell's electromagnetic theory, which led to the recognition of light as an electrical phenomenon and to many other grand generalizations, was more a mathematical than a physical theory. What it chiefly accomplished was to express, in mathematical language, the experimental results of Faraday. Maxwell, however, avoided giving any description of the molecular constitution of the media through which electrical energy was transmitted. Professor Fleming, in his pamphlet on The Electric Theory, says, "It seems tolerably clear from all the facts of electrolysis that electricity can only pass through a conducting liquid or electrolyte by being carried on atoms or groups of atoms which are called ions, for example, wanderers. The quantity thus carried by a hydrogen atom or other monad element such as sodium, silver, or potassium is a definite natural unit of electricity. The quantity carried by any other atom or group of atoms acting as an ion is always an exact integer multiple of this natural unit. This small indivisible quantity of electricity has been called by Dr. Johnstone Stoney an electron or atom of electricity. The artificial or conventional unit of electricity quantity in the centimeter-gram-second system, as defined by the British Association Committee on Electrical Units, is as follows. An electrostatic unit of electric quantity is the charge which, when placed upon a very small sphere, repels another similarly charged sphere, the centers being 1 centimeter apart, with a mechanical force of 1 dyne. The dyne is a mechanical unit of force, and is that force which, acting for 1 second on a mass of 1 gram, gives it a velocity of 1 centimeter per second. Hence, by the law of inverse squares, the force in dynes exerted by 2 equal charges, Q, at a distance, d, is equal to Q squared over d squared. 2 other units of electric quantity are in use. The electromagnetic unit, which is 30,000 million times as great as the electrostatic unit, and the practical unit, called the coulomb or ampere second, which is 3,000 million times the electrostatic unit. We can calculate easily the relation between the electron and the coulomb, that is, between nature's unit of electricity and the British Association unit, as follows. If we electrolyze any electrolyte, say acidified water, which yields up hydrogen at a negative electrode, we find that to evolve 1 cubic centimeter of hydrogen at 0 degrees Celsius, or 760 millimeters, we have to pass through the electrolyte a quantity of electricity equal to 8.62 coulombs. For 96,540 coulombs are required to evolve 1 gram of hydrogen and 11,200 cubic centimeters at 0 degrees Celsius, and atmospheric pressure weigh 1 gram. The number 8.62 is the quotient of 96,540 by 11,200. From various sources, calculations indicate that the number of molecules of hydrogen in a cubic centimeter is probably best represented by the number 20 million equals 2 times 10 to the 19th. Hence it follows, since there are two atoms of hydrogen in a molecule, that in electrostatic units, the electric charge on a hydrogen atom or hydrogen ion is 96,540 times 3 times 10 to the 9th divided by 11,200 times 4 times 10 to the 19th equals 65 over 10 to the 11th of a CGS electrostatic unit equals 22 over 10 to the 29th of a coulomb. Accordingly, if the above atomic charge is called 1 electron, then the conventional British Association electrostatic unit of electric quantity is equal to 1,540 million electrons, and the quantity called a coulomb is nearly 5 million electrons. The electron or the electric charge by a hydrogen atom or ion is evidently a very important physical constant. It is, in fact, nature's unit, from which all other physical units may be brought into agreement with natural quantities, and thus we see that electricity is atomic in nature and in structure. That is to say, we can have only in amounts which are all exact multiples of a certain unit, which unit cannot be subdivided, and 1,540 millions of these units equal 1 coulomb. For long it was held that the atom of matter was the smallest particle in nature and indivisible, but now we must assume that atoms are composed by smaller particles. We are compelled by all known facts to admit that Professor Crookes was right when he declared the cathode rays to be a stream of matter shot from the cathode. Professor J.J. Thomson, by measuring the deflection of the stream, of radiant matter, as Crookes called it, in a known magnetic field, shows that, if the radiant matter consists of corpuscles or particles, each carries a charge of 1 electron, and has a mass of about 1/1000th of a hydrogen atom, and their velocity is from 1/5 to 1/3 the velocity of light. So far as the effects in high vacua are concerned, Professor Crookes discovered all we know about cathode rays, but Lenard conceived the idea that these rays could penetrate the walls of the vessel containing the vacuum, and by inserting a window of aluminum in the vessel, he found the rays penetrated the aluminum, and that they are active outside the vessel as they are inside. Electrons are found in the mass of gas through which Röntgen rays have passed. Röntgen discovered that if the rays from the cathode struck a conductor in the vacuum bulb, that they penetrated the glass bulb enclosing the vacuum, and that they also penetrated many opaque bodies outside and produced photographs on active plates. The atom, it seems, can be divided into two parts of very unequal size. The small part is negatively electrified and is always the same, no matter from what chemical atom it comes. The remaining larger part is positively electrified, but is different in nature depending on the elementary atom broken up. It is not settled whether the particle and its negative charge are separable. It is, however, becoming common to speak of the two together as the electron. From this point of view, the theory of electricity is called the electronic theory. The principal objects of consideration in this theory are these electrons, which constitute what we call electricity. An atom of matter in its neutral condition has been assumed to consist of an outer shell or envelope of negative electrons associated with some core or matrix, which has an opposite electrical quality, such that if an electron is withdrawn from the atom, the latter is left positively electrified. A neutral atom minus an electron constitutes the natural unit of positive electricity, and the electron and the neutral atom minus an electron are sometimes called negative and positive ions. Deferring for a moment a further analysis of possible atomic structure, we may say that, with the above hypothesis in hand, we have then to express our statements of electrical facts in terms of the electron as the fundamental idea. On this theory, the difference between conductors and non-conductors is accounted for by assuming that an electric current is a procession of electrons, so that the conductor is a substance through which electrons can easily move. In nonconductors, the electrons may be moved or vibrated or displaced to some extent, but spring back again into their former place. The electronic or any theory must account for the waves set up in the ether around a variable current. This is explained on the hypothesis that a moving or vibrating electron, while its motion is being accelerated or reduced, radiates ethereal waves, and that a flying column of electrons produces a magnetic field and circles round the moving electrons as a center. The electron theory has not yet been fully developed. Many things about it are not clear, but most scientists are agreed upon the existence of the electron and are awaiting the results of further experiments to help them decide upon its exact nature and behavior. End of section 16.
Section 17 of the Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 2, Electrostatics, Atmospheric Electricity. Part 1. In the early days of electrical science, many of the experiments in electrostatics were developed, which still form a considerable part of the course usually taught in present-day schools. The attraction of amber when rubbed for light bodies was known to the ancient Greeks as long ago as 600 BC. About the year 1600, Gilbert, who had made several discoveries concerning the properties of the magnet, discovered in glass, sulfur, resin, and various precious stones the same attractive power known to be possessed by amber. From that time, innumerable physicists have extended Gilbert's discoveries and have found a great number of curious phenomena previously entirely unknown, and in this way have contributed to found that branch of physics which, under the name of electricity, has attained such important dimensions in modern times. If he had used a ball of glass or sulfur previously rubbed, suggests Guillemin, he would have known of the reciprocity of attraction, in the same way as he had shown that soft iron attracts a magnet. But Gilbert greatly extended the list of bodies capable, like amber, of being electrified by friction to those that we have already mentioned. He added shellac, rock, salt, alum, and rock crystal. He also found that electrical attraction took place not only between light bodies, but between certain solid bodies, drops of liquid, gaseous bodies, and dense vapors. Again, he discovered the influence of atmospheric conditions on electric phenomena. Boyle discovered the reciprocity of attraction between non-electrified bodies and electrified bodies. A very simple experiment on the mechanical principle of action and reaction being equal and opposite led to this discovery. On a pivot was placed a small shellac needle, electrified by being rubbed by catskin. Then, on holding his finger near one end, he found the needle drawn toward his finger. Otto von Guericke, who made the first frictional electrical machine, was the first to observe the phenomena of repulsion, and he also drew from the globe of sulfur of his machine visible sparks, accompanied by a crisp crackling sound, which was in fact the noise of the electric discharge. Here we had for the first time in these early experiments the production of sparks similar to those which constitute the electric arc, though it is a long step from these feeble sparks to the dazzling splendor of the electric light. The experiments of the celebrated Burgomeister of Magdeburg date from the middle of the 17th century. At the commencement of the 18th century, that was to witness such brilliant discoveries in electricity, Dr. Wall succeeded in producing most vivid sparks and far louder crackling. He also had some ideas of the great discovery which made Franklin so celebrated. "This light and that crackling," said he, "are the same thing as thunder and lightning." The analogy was indeed striking, and it was not long before it was verified and confirmed. Numerous observations on the electrical phenomena were due to Hauksbee. Among them are very interesting experiments on the light which is produced in a vacuum or in a rarefied medium when one introduces some bodies into it, and develops on their surface electricity by friction, or when one excites the exterior of the globe of glass, the interior of which is a vacuum. He observed in particular the effect of heat on the development of both attractive and repulsive forces. The attractions and repulsions of pieces of tinsel by a tube of glass rubbed with paper were found to be more energetic when the glass had been heated by friction. The effects of moisture and warmth that Gilbert had discovered were proved beyond doubt by the experiments of Hauksbee, Dufay, and Gray. The following passage occurs in Hauksbee's physico-mechanical experiments. When the tube became hottest by the strongest attrition, the force of the effluvia was rendered manifest to another sense too, namely that of feeling. They did not then only produce all the forementioned effects in a more remarkable manner, but were also plainly to be felt upon the face, or any other tender part, if the rubbed tube was held near it, and they seemed to make very nearly such sort of strokes upon the skin, as a number of fine limber hairs pushing against it might be supposed to do. The discovery of electrical conductivity was made in the early part of the 18th century by Stephen Gray. While looking for the reason of the difference between the two classes, he came upon the general fact that all bodies, without exception, are capable of being electrified, but that the circumstances must be varied to suit the substances. Let us rapidly review the points that led Gray to this important discovery. Having electrified a piece of glass tube, the ends of which were stopped with corks, he was surprised to find that the corks, which he had not rubbed, picked up the light bodies just as the tube itself did, showing that the electricity passed from the glass to the cork. Gray followed up on this experiment by lengthening the corks with sticks of ivory, wood, or metal, yet he had the same phenomena even with stems which ended in a ball of ivory. Hung from a balcony by a long cord fastened to the tube, the ball still was electrified. He then varied his experiment to greater and greater distances until he found the same effect at the end of a cord 765 feet long. But Gray found that in order to succeed, certain conditions had to be fulfilled. The cord which carried the electricity had to be suspended by silk strings, as he found that he got no electrification at all if he suspended it by means of metal wires. One more experiment of Gray's that was soon repeated in all laboratories was to show that the human body conducts electricity. It explains the impossibility that has always been found in trying to electrify such substances as the metals. Having suspended a child by hair cords, and having touched him with his electrified tube, he found that all parts of the child's body had acquired the power of attracting light bodies. The same effect was produced when the child stood on a cake of electric substance, such as a resin, as was produced when he was suspended by the hair cords. From these experiments, which were then varied in innumerable ways, two very important conclusions were drawn. The first, that electricity obtained by friction could be transmitted to a distance through any substance that could not itself be electrified. The second, a corollary to the first, that this transmission is impossible or very difficult if the transmitting body is one of those capable of being electrified by the method described above. We quoted above Gray's first experiment, which established the electrical conductivity of the body. It was a French physician, Dufay, a member of the Academy of Sciences, who drew the first spark from the human body. Being suspended by silk cords, he found when electrified that if anyone brought his knuckle near to him, he felt a stinging sensation like a pinprick, also that the person's knuckle felt the same sensation. When the experiment was performed in the dark, a little spark was observed. Gray took up the experiments of Dufay, and in his turn found that he could draw sparks from any insulated body which had been put into contact with rubbed glass, if these bodies terminated in a point. A small luminous cone was seen, accompanied by a slight noise. In reference to this, Gray repeated Wall's comparison between the spark, followed by the crackling sound, and the lightning, followed by thunder. Newton's grand discovery of the law of the universal attraction of matter when he showed that the force was proportional to the mass and that it varied in the inverse ratio of the square of the distance, incited the physicists of the 18th century to discover the law which governed the strength of electrical forces. Dufay, Hauksbee, Muschenbrock, Aepinus, and Cavendish were all more or less instrumental in attaining this end, but we are indebted to Coulomb for an exact experimental demonstration of these laws. Coulomb used for this purpose a similar apparatus to the magnetic balance. From the figure it will be seen that it consisted of two spheres so arranged that they could be charged and the force of repulsion between them balanced by the torsion of the suspension. By means of this instrument, Coulomb was able to prove the two laws of electrical attraction. 1. The repulsion between two electrified bodies charged with the same electricity varies inversely as the square of the distance between them. 2. The attractions and repulsions vary in the ratio of the products of the quantities of free electricity, that is to say, of the electric charges of the two bodies. The action of points on metallic conductors, in increasing the density of the charge at the point, received the attention of Franklin. The following quotation from his Experiments and Observations on Electricity made at Philadelphia, 1774, describes Franklin's own experiments on this subject. Place an iron shot of 3 or 4 inches diameter on the mouth of a clean dry glass bottle. By a fine silken thread from the ceiling, right over the mouth of the bottle, suspend a small cork ball about the bigness of a marble. The thread of such a length is that the cork ball may rest against the side of the shot. Electrify the shot, and the ball will be repelled to the distance of 4 or 5 inches, more or less, according to the quantity of electricity. When in this state, if you present to the shot the point of a long, slender, sharp bodkin at 6 or 8 inches distance, the repellency is instantly destroyed and the cork flies to the shot. A blunt body must be brought within an inch and draw a spark to produce the same effect. To prove that the electrical fire is drawn off by the point, if you take the blade of the bodkin out of the wooden handle and fix it in a stick of sealing wax, and then present it at the distance aforesaid, or if you bring it very near, no such effect follows, but sliding one finger along the wax till you touch the blade, and the ball flies to the shot immediately. If you present the point in the dark, you will see sometimes at a foot distance and more a light gather upon it, like that of a firefly or glowworm. The less sharp the point, the nearer you must bring it to observe the light, and at whatever distance you see the light, you may draw off the electrical fire and destroy the repellency. If a cork ball so suspended be repelled by the tube, and a point be presented quick to it, 'tis surprising to see how suddenly it flies back to the tube. Points of wood will do near as well as those of iron, provided the wood is not dry, for perfectly dry wood will no more conduct electricity than sealing wax. It is calculated that the density of electricity at an infinitesimally fine point would be infinitely great, since it is impossible to charge a pointed conductor in the air with electricity. This is proved by experiment. As fast as electrification is produced, it is given off the point into the air and disappears. When we examine the extremity of a point in the dark, there is seen a luminous crest. If while the point is in communication with the source of electrification, one places one's hand before it, a draft is at once perceptible, arising from the motions of the particles of air. This can still be better shown by holding a candle flame in front of a long-pointed conductor. The electric wind is sufficient to bend the flame sharply down or even to put it out. This movement of the air at points on electrified conductors has always been attributed to the accumulation of electricity, which has been compared to a fluid. But the following explanation seems to us preferable, as it involves no hypothesis on the nature of electricity, and besides, it is found to agree with known phenomena. The molecules of air in contact with a point electrified to a great electric density become charged with the same electrification as the conductor itself. Hence, the nearest molecules are repelled and others fill their place, which become electrified in their turn, and so on. Hence, the current of air, which only lasts as long as the electricity is being supplied. It can be stopped by putting a cap of sealing wax over the point. The explanation of the attraction of an electrified body for an unelectrified one was not well understood until the middle of the 18th century. John Canton of Stroud seems to have been the first to give the true explanation. His apparatus was similar to that shown in Figure 8. If the sphere C be charged with a positive charge of electricity, the end A of the cylinder, which is nearest to the sphere, will be charged negatively. The other end B will be charged positively. We can prove this if we bring an electrified pendulum near to each end in turn. Suppose the little ball to be charged positively is found to be attracted to the end A when brought carefully toward it, but when brought toward the end B, it is repelled. The reverse would be the case if the sphere C were charged negatively. It may be well here to point out the difference between a conductor and a dielectric or non-conductor. A conductor merely connects different parts of the dielectric which surrounds it and with which it is in contact. If therefore this dielectric be suddenly charged in one place, this charge cannot remain at that place because it is in contact with the conductor, but must flow into the conductor along it and then out into the dielectric surrounding it. And this takes place at every point of contact between the conductor and the dielectric. The office of the conductor, then, is to distribute the charge to the dielectric. If the conductor be spherical in shape, and there is no other charge nearby, the dielectric will be charged uniformly all about the sphere. If the conductor tapers to a point, the charge in the dielectric will be most intense about the point. Or if the charge about the sphere is influenced by a neighboring charge, the conducting sphere allows it to move as the charged body may dictate. This principle of electrical influence was soon made use of in constructing a machine for the production of electric charges, and which was the forerunner of the modern electrical influence machine. This was the electrophorus of Volta, who gave it the name of perpetual electrophorus, because it preserves for a long time the charges that it has received. It consists of two parts: a cake of insulating material, such as resin, sulfur, or India rubber, cast into a wooden or metal tray, and a metal disc fixed to an insulating handle of glass or to silk cords. Frequently, the disc is of smaller diameter than the cake, and sometimes it is made not of metal, but of wood, covered on both edge and faces with tinfoil. To use the electrophorus, remove the metal disc and rub the insulating cake with flannel, woolen cloth, or fur, best of all with a catskin. This produces negative electrification on the resinous cake. This you may prove if you bring your fingers near the cake, for you will observe small sparks and crackling sounds. Now take the metal disc by the insulating handle and place it on the rubbed insulating cake. Now pause a moment. Let us think what has happened in this action. While you were putting down the lid on the cake, even before it touched the cake, it was under influence. The cake is negative, hence, as you hold the lid over it, there will be a displacement and a rush of electricity in the lid, causing a positive charge to accumulate on the lower disc, leaving the upper side negative. This effect will, of course, increase as the disc is lowered. It will be noticed that the metal dish in which the cake stands is also under influence, but this is of no importance. You must now touch with your finger the top of the lid. Your finger will also be under influence during this action, a plus charge accumulating on its tip, and then discharging itself with a small spark to fill up and neutralize the minus charge on the top surface. Now, lift up the lid by the handle. You will find that it is positively electrified, and you can carry away the charge and use it to give a big spark to any other conductor. You can then put the lid down again on the cake, touch it, lift it up again, and take another spark as often as you please. the cake remaining all the time charged with its original charge. The length of the spark is roughly proportional to the size of the electrophorus. Maschart, in his treatise, said that Lichtenberg constructed an electrophorus with a cake 6 feet across, and the disk was 5 feet across, and the sparks drawn from it 14 to 16 inches long. Another very large electrophorus was made by Kleinworth for the University of Göttingen. The cake of resin was 2.25 meters in diameter, and the conducting disk 2 meters. The cake sometimes preserves its charge for months, if it be kept in a cupboard where the air is perfectly dry. We have said that the insulating cake of the electrophorus is made of resin, sulfur, or India rubber. All good insulators can be used. Mixtures of these substances are generally used in order to make the cake less brittle. End of section 17. Section 18 of the Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3, edited by Francis Rolt Wheeler. Electricity, Chapter 2. Electrostatics, Atmospheric Electricity. Part 2. A short description of the principal static machines which have been developed is taken from Professor S.P. Thompson's Elementary Lessons in Electricity and Magnetism. For the purpose of procuring larger supplies of electricity than can be obtained by the rubbing of a rod of glass or shellac, electric machines have been devised. All electric machines consist of 2 parts, one for producing, the other for collecting the electric charges. Experience has shown that the quantities of plus and minus electrification developed by friction upon the 2 surfaces rubbed against one another depend upon the amount of friction, upon the extent of the surfaces rubbed, and also upon the nature of the substances used. The earliest form of electric machine was devised by Otto von Guericke of Magdeburg, and consisted of a globe of sulfur fixed upon a spindle, and pressed with the dry surface of the hands while being made to rotate. With this he discovered the existence of electric sparks and the repulsion of similarly electrified bodies. Sir Isaac Newton replaced von Guericke's globe of sulfur by a globe of glass. A little later, the form of the machine was improved by various German electricians. Von Bose added a collector or prime conductor in the shape of an iron tube, supported by a person standing on cakes of resin to insulate them, or suspended by silken strings. Winkler of Leipzig substituted a leathern cushion for the hand as a rubber, and Gordon of Erfurt rendered the machine more easy of construction by using a glass cylinder instead of a glass globe. The electricity was led from the excited cylinder or globe to the prime conductor by a metallic chain, which hung over against the globe. A pointed collector was not employed until after Franklin's famous researches on the action of points. About 1760, Delafonde, Planta, Ramsden, and Cuthbertson constructed machines having glass plates instead of cylinders. All frictional machines are, however, now obsolete, having in recent years been quite superseded by the modern influence machines. The cylinder electric machine consists of a glass cylinder mounted on a horizontal axis capable of being turned by a handle. Against it is pressed from behind a cushion of leather stuffed with horsehair, the surface of which is covered with a powdered amalgam of zinc or tin. A flap of silk attached to the cushion passes over the cylinder, covering its upper half. In front of the cylinder stands the prime conductor, which is made of metal, and usually of the form of an elongated cylinder with hemispherical ends mounted upon a glass stand. At the end of the prime conductor nearest the cylinder is fixed a rod bearing a row of fine metallic spikes resembling in form a rake. The other end usually carries a rod terminated in a brass ball or knob. When the handle is turned, the friction between the glass and the amalgam-coated surface of the rubber produces a copious electrical action, electricity appearing as a plus charge on the glass, leaving the rubber with a minus charge. The prime conductor collects this charge by the following process. The plus charge being carried around on the glass acts inductively on the long insulated conductor, repelling a plus charge to the far end and leaving the nearer end minusly charged. The effect of the row of points is to emit a minusly electrified wind toward the attracting plus charge upon the glass, which is neutralized thereby, the glass thus arriving at the rubber in a neutral condition, ready to be again excited. This action of the points is sometimes described, though less correctly, by saying that the points collect the plus charge from the glass. If it is desired to collect also the minus charge of the rubber, the cushion must be supported on an insulating stem and provided at the back with a metallic knob. It is, however, more usual to use only the plus charge and to connect the rubber by a chain to the earth, so allowing the minus charge to be neutralized. The friction of a jet of steam issuing from a boiler through a wooden nozzle generates electricity. In reality, it is the particles of condensed water in the jet which are directly concerned. Sir W. Armstrong, who investigated this source of electricity, constructed a powerful apparatus known as the hydroelectrical machine, capable of producing enormous quantities of electricity and yielding sparks 5 or 6 feet long. The collector consisted of a row of spikes placed in the path of the steam jets issuing from wooden nozzles, and was supported together with a brass ball which served as a prime conductor upon a glass pillar. After the invention of the electrophorus by Volta, the idea naturally suggested itself of performing mechanically the several operations of bringing the plate near the charged bed, of touching its upper side, and of removing it to a large metallic body where the charge could be stored. One of the first of these mechanical arrangements was the revolving doubler of Nicholson, invented in 1788, consisting of a revolving apparatus in which an insulated carrier can be brought into the presence of an electrified body, there touched for an instant while under influence, then carried forward with its acquired charge toward another body, to which it imparts its charge, and which in turn acts inductively on it, giving it an opposite charge, which it can convey to the first body, thus increasing its initial charge at every rotation. In the modern influence machines, 2 principles are embodied. 1. The principle of influence, namely that a conductor touched while under influence acquires a charge of the opposite kind. And 2. The principle of reciprocal accumulation. This principle must be carefully noted. Let there be 2 insulated conductors, A and B, electrified ever so little, one positively, the other negatively. Let a third insulated conductor, C, which will be called a carrier, be arranged to move so that it first approaches A and then B, and so forth. If touched while under the influence of the small positive charge on A, it will acquire a small negative charge. Suppose that it then moves on and gives this negative charge to B. Then let it be touched while under the influence of B, so acquiring a small positive charge. When it returns toward A, let it give up this positive charge to A, thereby increasing its positive charge. Then A will act more powerfully, and on repeating the former operations, both B and A will become more highly charged. Each accumulates the charges derived by influence from the other. This is the fundamental action of the machines in question. The modern influence machines date from 1860, when C.F. Varley produced a form with 6 carriers mounted on a rotating disc of glass. This was followed in 1865 by the machine of Holtz and that of Topler, and in 1867 by those of Lord Kelvin, the replenisher and the mouse mill. The latest forms are those of Mr. James Wimshurst. At the present time, these machines are used to a limited extent as a source of high voltages for such work as operating vacuum tubes, X-ray apparatus, and the like. But their uncertainty of action, small power, and the irregularity of their discharge make the high-tension transformer or Ruhmkorff coil preferable. Cuneus, a pupil of Muschenbroek, a celebrated physicist of the 18th century, was one day trying to electrify some water in a wide-necked bottle. For this purpose he held the bottle in one hand, after having placed in the bottle a metal rod connected to the machine. When he thought that the water was sufficiently electrified, he tried to remove the iron rod with one hand without losing his hold of the bottle with the other hand. He received a shock that surprised him. Muschenbroek repeated Cuneus's experiment, but the shock that he received in his arms, shoulders, and chest was so great that he lost consciousness and was so frightened that in writing to Reaumur about this then new discovery, he wrote that for nothing in the world, not even for the crown of France, would he go through it again. But some other physicists were less fearful. Allemann, Lemonnier, Winkler, and the Abbé Nollet varied the experiment in all sorts of ways, and so a new piece of apparatus was added to the electrical science. This apparatus, called the Leyden jar, is named after the place where the experiment was first performed in 1746. The Leyden jar is only a form of electric condenser, the essential properties of which have already been explained in connection with Maxwell's theory. It is again to Franklin that science is indebted for an experiment which shows where the charge in such a jar resides. Franklin constructed a Leyden jar having both internal and external metallic coatings removable. Having fitted them to the jar, he connected the inner coating with an electrical machine and the outer coating with the earth. He charged the jar in the usual manner. He then separated the metallic coatings on the jar, and examining each one for electrification, he found the metallic coatings practically unelectrified, while the glass jar proved to be highly electrified. Upon replacing the coatings in the jar, he was able to obtain a bright spark, just as though the coatings had not been removed. This experiment clearly proved that the important part of such a Leyden jar, or condenser, was the glass, or the dielectric, and that the function of the conducting coatings was merely to spread the charge over the glass. Taking such a view, it will be readily seen that the larger the jar, the greater is the quantity of electricity which may be stored therein. Large jars, however, are often inconvenient to handle, so that a battery of such jars is used, having their inner coatings all connected together to form one large coating, and the outer ones similarly connected. Figure 10 shows such a battery, the outer coatings being connected by the tinfoil lining of the box. From time to time it has been attempted to use for the dielectric materials other than glass, and thousands of condensers using a paraffined paper are in use on modern telephone and telegraph circuits. Larger condensers are used on power circuits. None of these other materials is, however, as satisfactory as glass, being liable to be disrupted if the pressure of the charge is too great. The opportunities for using condensers to advantage are rapidly increasing at present, and considerable energy is being directed toward their development. The desirable qualities of such a condenser are that its dielectric should be capable of containing a very large charge, that it should stand very high electric pressure without disruption, and that its coatings should be in the most intimate contact with the dielectric. In some recent condensers made in Switzerland, the metal coatings are made by chemically depositing silver upon the inner and outer surfaces of the glass. The ancients, who knew nothing of electricity, could not conceive of thunder as anything but the result of a purely mechanical shock. Seneca, speaking of the fact that two hands struck together produced a loud noise, concluded from that the collision of two enormous clouds ought to sound with a very great crash. Again, he compares thunder, the sound of which is very sharp, even penetrating, to the noise made by the bursting of a bladder on a person's head. Lucretius also explains thunder by the shaking of the clouds, or their tearing asunder. The identity of lightning with electricity was first shown by Benjamin Franklin in a paper published in 1749, 2 years before his experiments with the storm clouds. At that epoch he had just recognized the power of points. 2 ingenious experiments in which this power was put into play furnished him with a new analogy and suggested to him to verify by the storm clouds the truth of his conjectures. Having suspended by silk threads to the ceiling of his room a tube of gilt paper 10 feet in length and a foot in diameter, Franklin charged it with electricity. Then, presenting to the tube at the distance of a foot the point of a needle, the tube was instantly discharged. If, on the contrary, he presented to it a blunt body, an iron bolt or punch rounded at the end, he found it was necessary to put it within 3 inches before it could cause the discharge, which then, he said, took place with a sudden crackling. Suspending in the same way some great brass scales, the pans of which were supported by silk cords a foot from the floor, he electrified one of the pans. The twisting of the suspending cord caused the scales to turn. He placed the iron punch underneath, below a point of the circumference described. When the pan which was electrified passed over it, it lowered itself, came in contact with it, and thus discharged itself. But if the end of the punch was furnished with a needle, the point uppermost, the pan passed above it without approaching, and the discharge took place silently. Or if in its course the pan had come near enough for a spark to strike, it could not, because it would have been discharged beforehand. Now, says Franklin, if the fire of electricity and that of lightning be the same, as I have endeavored to show at large in a former paper, this pasteboard tube and these scales may represent electrified clouds. If a tube only 10 feet long will strike and discharge its fire on the punch at 2 or 3 inches distance, an electrified cloud of perhaps 10,000 acres may strike and discharge on the earth at a proportionally greater distance. The horizontal motion of the scales over the floor may represent the motion of the clouds over the earth, and the erect iron punch a hill or high building. And then we see how electrified clouds passing over hills or high buildings at too great a height to strike may be attracted lower still within their striking distance. And lastly, if a needle fixed on the punch with its point upright, or even on the floor below the punch, will draw the fire from the scale silently, at a much greater than the striking distance, and so prevent its descending toward the punch. Or if in its course it would have come nigh enough to strike, yet being deprived of its fire it cannot, and the punch is thereby secured from the stroke. I say, if these things are so, may not the knowledge of this power of points be of use to mankind in preserving houses, churches, ships, etc., from the stroke of lightning, by directing us to fix on the highest parts of those edifices upright rods of iron made sharp as a needle and gilt to prevent rusting, and from the foot of these rods a wire down the outside of the building into the ground, or down round one of the shrouds of the ship, and down her side till it reaches the water? Would not these pointed rods probably draw the electrical fire silently out of a cloud before it came nigh enough to strike, and thereby secure us from that sudden and most terrible mischief? And thus it is that this discovery of Franklin's has been the means of saving much property from destruction. It is only of recent years that much has been added to the knowledge of the action of lightning rods and of their proper design and application. Hertz's experiments in electrical oscillations and the proof that lightning discharges were also oscillatory in their character enabled us to gain a better understanding of how to handle these tremendous discharges. It is now known that lightning discharges have a frequency of oscillation of about 500,000 periods per second. A recent and most beautiful application of condensers to the conduction of these lightning discharges to Earth may not be out of place here. If a lightning discharge strikes an electric line in its course to Earth, it may find it easier to pass back to the generator at the power station, jump through the insulation to the frame and then to the Earth, then to leap over the insulators and down the pole to the Earth, the result being to destroy the generator. If, however, condensers are connected at various points along the line, it may be well to see what should happen. Every time that a condenser is charged and discharged, a current flows through the wire leading to it, one way on charging, the other on discharging. If this succession of charges and discharges takes place slowly, only a small amount will flow into and out of the condenser, but if it takes place rapidly, the current is proportionately increased, without the pressure being any higher. Suppose such condensers to be connected on a line in which the current has a frequency of 60 oscillations or cycles per second. A small current will then flow continually. This current is of such a character that it does not mean a waste of power, but this is too advanced to be here explained. If, however, a lightning discharge having a frequency of 500,000 per second strikes the line, it will pass readily to Earth through the condensers instead of disrupting the insulation of the generators, the condensers being able to pass 500,000 divided by 60 as much current as would be passed from the line. There is still much to be learned of electrical disturbances in the atmosphere, and little is yet known of the causes producing them. It is a field of vast possibilities, and one whose study may result in giving man a partial control over atmospheric conditions. End of section 18. Section 19 of the Science History of the Universe, Volume 3. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 3. Edited by Francis Rolt Wheeler. Electricity, Chapter 3. Fundamental Discoveries. There are in all sciences some discoveries which seem to open vast fields for exploration, and which appear suddenly to increase the power of mankind. In electrical science, the benefits conferred by the discoveries of Volta and Galvani, Davy, Arago, Ampere, Faraday, Seebeck, Maxwell, and Hertz are only just beginning to be realized. Volta and Galvani started the investigation of electric currents, and today the Earth is full of applications of them, each one the servant of a human brain. Each day sees a new device based upon them, and each application presents them in a new light, which again leads to another useful appliance of the principles involved. 100 years ago, men were not so well organized for scientific research as they are at present, and it may seem strange that such a simple discovery as electromagnetic induction should have taken so long to develop after the production of electric currents. It must be remembered, however, that organization was loose, not bound tightly together as it is now, when mankind is, as it were, united into one large concentrated brain. If a discovery is made at the present time, the whole world knows of it in a few days, and thousands of men stand ready to apply it to all kinds of industries, and many men can bring their vast experience to the immediate aid of the discoverer, so that the discovery is quickly perfected. All this power of self-improvement is owed, however, to those whose work have united men so closely. Scientific research has developed into a business. Large companies have gathered together the best brains of the world. Money and conveniences are placed at their disposal. The needs of industry are presented to them and are quickly filled. The scientific brain is kept in constant touch with the wants of life, and there is at last accomplished that union of the scientist and the man of the world. The one with needs, the other with the means of fulfilling them. That was lacking in the earlier days. There are in general two classes of scientists. One is possessed of a mathematical mind, delighting in the abstract solution of a problem and caring not whether the result turns out one way or another. He is concerned rather with the proof of the similarity of processes than with any difference of detail. To the man with the mechanical mind, however, the detection of differences is all important. He finds his pleasure in observing differences in phenomena by the process of experiment, and his whole idea is to obtain a definite and useful result. Both classes of men are necessary. Maxwell developed a beautiful mathematical theory of great comprehensiveness, but the proofs waited for the experimental demonstrations of Hertz. The groundwork of the science is, however, usually developed Through that property of so few minds, the power of observation, the discovery of the electric current was an event. Galvani, an eminent doctor and professor of anatomy at the University of Bologna, was one evening in the year 1780 busy in his laboratory with some friends, making experiments relating to a nervous fluid in animals. On a table where there was an electric machine used for the experiments, there had been placed by chance some recently skinned frogs intended to make broth of. One of Galvani's assistants, says Pierre Sue in his Histoire du Galvanisme, casually put the point of his instrument near the internal cruel nerves of one of the animals. Immediately all the muscles of the limbs seemed to be agitated with strong convulsions. Galvani's wife was present. She was struck with the novelty of the phenomenon. She thought she saw that it occurred just at the moment when a spark was taken from the electric machine. She warned her husband, who hastened to verify this curious fact, and he recognized that the muscular contractions of the frog took place, in fact, every time that a spark appeared, but ceased while the machine was at rest. This observation was the beginning of many experiments with the doctor by which he tried to prove the identity of the nervous fluid of animals with the supposed electric fluid. In 1786, he again continued researches of this kind. Being anxious one day, says Amédée Guillemin in his Electricity and Magnetism, to see whether the influence of atmospheric electricity on the muscles of frogs would be the same as that produced in machines, he had for that purpose hung up a number of skinned frogs' legs on the balcony of a terrace of his house. He hooked the hind legs to the iron of the balcony by a copper wire, which passed under the lumbar nerves. Galvani remarked with surprise that every time that the feet touched the balcony, the frog's limbs were contracted with quick convulsions, though at that moment there were no signs of a stormy cloud and therefore no particular electric influence of the atmosphere. These facts suggested to Galvani the idea that there existed an electricity belonging to animals, inherent in their organization, that this electricity, secreted by the brain, resides specially in the nerves, by which it is communicated to the entire body, that the principal reservoirs of this electricity are the muscles, each fiber of which may be considered as having two surfaces, and possessing by that means the two electricities, positive and negative, each one of them representing, besides, so to speak, a small Leyden jar, of which the nerves are the conductors. Hence the comparisons he makes between the muscular contractions in frogs and other animals, and the commotions produced by the discharge of a Leyden jar. Alexander Volta, then professor of natural philosophy at Pavia, repeated Galvani's experiments, but he very soon modified his explanations. According to Volta, the electricity developed was of the same nature as that which an electric apparatus produces. It is the contact between dissimilar metals which gives place to the production of electricity, one of the metals being charged with a positive, the other with a negative electrification. These charges combine in traversing the middle conductor of muscles and nerves. Then arose between the two celebrated philosophers a discussion, a struggle, honorable to both and above all profitable to science, which thereby became enriched by a multitude of new facts. The invention of the marvelous apparatus which received the name of voltaic pile at last caused the theory of the professor of Pavia to prevail, though Galvani's hypothesis on the existence of a sort of animal electricity is now recognized as partly true. On the other hand, Volta's ideas have been somewhat modified. The outcome of these contentions was the invention of Volta's pile, first made in 1800. Here, for the first time, was produced a means of generating a steady and continuous flow of electric current. Volta's construction was as follows. Discs of copper, zinc, and flannel were cut out and arranged in a pile in the order copper, flannel, zinc. and this order was successively repeated, the flannel being first dipped in sulfuric acid so that its function was merely to connect the copper and zinc by the acid. This arrangement gave a feeble electromotive force between the elements of each set, which increased when one connection was made at the lower end of the pile and the other was moved toward the top. Volta's idea of the action of the pile was, however, not as it is known today. He believed that the source of the electromotive force was at the contact of the copper and the zinc disks, and that the moistened cloth served merely as a means of connecting them, whereas the real seat of this force is at the contact of the acid with the zinc. This discovery of Volta's was the starting point of many investigations, in which the metals and the liquids were tried in all sorts of combinations, many of which were quite successful, and soon batteries were developed which were capable of furnishing quite powerful currents. For 60 years, these batteries were the only source of current available for conducting the brilliant experiments of that period. As soon as a source of current was obtainable, it was natural to ascertain the effects of this current on various bodies. One of the first of these was that of Carlisle and Nicholson in 1800 on the decomposition of water. Having passed the current of a voltaic pile formed of disks of silver and zinc through water, they noticed that at the end of the copper wire, which came from the negative pole of the pile, some gaseous bubbles were given off, which they ascertained to be hydrogen. The other wire became rapidly oxidized. On substituting for copper platinum, which is not attacked by oxygen, bubbles of this latter gas were given off in the same way from the positive wire. That is to say, when the two platinum wires were used, oxygen was given off in bubbles from the surface of the wire by which the current entered the water. The hydrogen gas was at the same time given off in bubbles from the surface of the wire by which the current left the water. The next fact of great importance was brought to light 20 years after the discovery of Volta's pile by Ørsted, professor in the University of Copenhagen. This accomplished savant found that the electric current acted on the magnetic needle. For a long time, says Guillemot, there had been a suspicion of the existence of a relation between magnetic phenomena and electricity. People had remarked the occurrence of perturbations by the mariner's compass on ships struck by lightning, or when their masts presented the phenomenon known by the name of St. Elmo's fire. It was known that discharges of batteries of Leyden jars affected magnetic needles placed near the apparatus. But these facts only gave vague ideas on the relation mentioned above. In 1820, the year after that in which Ørsted made his discovery, Ampere studied and described the laws of this action, and showed besides that the current themselves acted on currents, and later Arago, Davy, and Sturgeon discovered the magnetizing of steel and soft iron under the influence of the current from a battery. The experiments of these men were so many points of departure for a multitude of new experiments which in a short time completely changed the aspect of this part of the science by showing that magnetism and electricity are different manifestations of the same cause. Ørsted expressed his discovery by saying that a current acts in a revolving manner on a magnetic needle. He does not, however, seem to have understood that the electric current carried about it a magnetic field, and that it was the mutual action of this field and of the magnetism in the needle that produced the deflection. Ørsted expressed the law of the deflection as follows. When an electric current acts on the magnetic needle, the north pole of the needle is urged toward the left of the current. Ampere was the first to use Ørsted's discovery to measure the intensity of currents, but to Schweiger and to Poggendorff, working independently, is due the happy thought of multiplying the action of electricity on the magnetizing needle so as to detect the existence of the feeblest current. This instrument, then termed the multiplier, is now called the galvanometer, and its importance as a factor in the further development of the science is seldom appreciated. From this developed the Thomson galvanometer, in which the needles were made extremely small and light, and having a mirror attached, upon which a beam of light was thrown, and the reflected beam was made to pass over a scale. The galvanometer was thereby furnished with a long weightless pointer whereby the smallest motion of the needle was multiplied many times, and extremely small currents could be detected. In September 1820, a little while after the discoveries of Oersted and Ampere, Arago made the following experiment. He plunged into a mass of iron filings a copper wire which was connected to the two poles of a battery. On drawing out the wire, without interrupting the current, he found it to be covered over its whole surface with particles of filings arranged transversely. As soon as the current was broken, the iron particles became detached from the copper and fell down. To assure himself that this was really temporary magnetism and not the attraction of an electrified body for light bodies, he substituted for the iron filings a non-magnetic substance, such as copper dust or powdered glass, and found that the phenomenon did not take place. On placing needles of soft iron, and then of tempered steel, very near the copper wire and across it, he saw that the action of the current transformed them into magnetic needles, having their south poles always to the left of the current, a result in conformity with the earliest experiments of Oersted. Shortly afterward, Arago and Ampere noticed that magnetism of iron or steel is developed much more energetically by placing the needle inside a spiral coil of wire through which the current flows. This was the origin of the electromagnet, which was later developed by Sturgeon and Henry. The discovery of the greatest value to electrical science was that made by Faraday in 1831. He reasoned that if magnetism could be produced by the action of the electric current, the converse should also be true, and after some experimenting he was successful in demonstrating it. An interesting account of his experiments is given below, being an extract from Professor Tyndall's Faraday as a Discoverer. In 1831, we have Faraday at the climax of his intellectual strength, 40 years of age, stored with knowledge, and full of original power. Through reading, lecturing, and experimenting, he had become thoroughly familiar with electrical science. He saw where light was needed and expansion possible. The phenomena of ordinary electric induction belonged, as it were, to the alphabet of his knowledge. He knew that under ordinary circumstances, the presence of an electrified body was sufficient to excite, by induction, an unelectrified body. He knew that the wire which carried an electric current was an electrified body, and still that all attempts had failed to make it excite in other wires a state similar to its own. What was the reason of this failure? Faraday could never work from the experiments of others, however clearly described. He knew well that from every experiment issues a kind of radiation, luminous in different degrees to different minds, and he hardly trusted himself to reason upon an experiment that he had not seen. In autumn of 1831, he began to repeat the experiments with electric currents, which up to that time had produced no positive result. And here, for the sake of younger inquirers, if not for the sake of us all, it is worthwhile to dwell for a moment on a power which Faraday possessed in an extraordinary degree. He united vast strength with perfect flexibility. His momentum was that of a river, which combines weight and directness with the ability to yield to the flexures of its bed. The intentness of his vision in any direction did not, apparently, diminish his power of perception in other directions. And when he attacked a subject, expecting results, he had the faculty of keeping his mind alert, so that results different from those which he expected should not escape him through preoccupation. He began his experiments on the induction of electric currents by composing a helix of two insulated wires, which were wound side by side round the same wooden cylinder. One of these wires he connected with a voltaic battery of 10 cells and the other with a sensitive galvanometer. When connection with the battery was made, and while the current flowed, no effect whatever was observed at the galvanometer. But he never accepted an experimental result until he had applied to it the utmost power at his command. He raised his battery from 10 cells to 120 cells, but without avail. The current flowed calmly through the battery wire without producing, during its flow, any sensible result upon the galvanometer. During its flow, and this was the time when an effect was expected. But here Faraday's power of lateral vision, separating, as it were, from the line of expectations, came into play. He noticed that a feeble movement occurred when he made contact with the battery, that the needle would afterward return to its former position and remain quietly there unaffected by the flowing current. At the moment, however, when the circuit was interrupted, the needle again moved, and in a direction opposed to that observed of the completion of the circuit. This result and others of a similar kind led him to the conclusion, in his own words, that the battery current through the one wire did in reality induce a similar current through the other, but that it continued for an instant only, and partook more of the nature of the electric wave from a common Leyden jar than of the current from a voltaic battery. The momentary currents thus generated were called induced currents, while the current which generated them was called the inducing current. It was immediately proved that the current generated at making the circuit was always opposed in direction to its generator, while that developed on the rupture of the circuit coincided in direction with the inducing current. It appears, says Tyndall, as if the current on its first rush through the primary wire sought a purchase in the secondary one, and by a kind of kick impelled backward through the latter an electric wave, which subsided as soon as the primary current was fully established. Faraday for a time believed that the secondary wire, though quiescent when the primary current had been once established, was not in its natural condition, its return to that condition being declared by the current observed at breaking the circuit. He called this hypothetical state of the wire the electrotonic state. He afterward abandoned this hypothesis, but seemed to return to it in afterlife. The term electrotonic is also preserved by Professor Dubois-Raymond to express a certain electric condition of the nerves, and Professor Clerk Maxwell has ably defined and illustrated the hypothesis in the 10th volume of the Transactions of the Cambridge Philosophical Society. The mere approach of a wire forming a closed curve to a second wire, through which a voltaic current flowed, was then shown by Faraday to be sufficient to arouse in the neutral wire an induced current. The withdrawal of the wire also generated a current having the same direction as the inducing current. Those currents existed only during the time of approach or withdrawal, and when neither the primary nor the secondary wire was in motion, no matter how close their proximity might be, no induced current was generated. Faraday, remarks Tyndall, has been called a purely inductive philosopher. A great deal of nonsense is, I fear, uttered in this land of England about induction and deduction. Some profess to befriend the one, some the other, while the real vocation of an investigator, like Faraday, consists in the incessant marriage of both. He was at this time full of the theory of Ampere, and it cannot be doubted that numbers of his experiments were executed merely to test his deductions from that theory. Starting from the discovery of Oersted, the celebrated French philosopher had shown that all the phenomena of magnetism then known might be reduced to the mutual attractions and repulsions of electric currents. Magnetism had been produced from electricity, and Faraday, who all his life long entertained a strong belief in such reciprocal actions, now attempted to effect the evolution of electricity from magnetism. Round a welded iron ring, he placed two distinct coils of covered wire, causing the coils to occupy opposite halves of the ring. Connecting the ends of one of the coils with a galvanometer, he found that the moment the ring was magnetized, by sending a current through the other coil, the galvanometer needle whirled round 4 or 5 times in succession. The action, as before, was that of a pulse which vanished immediately. On interrupting the current, a whirl of the needle in the opposite direction occurred. It was only during the time of magnetization or demagnetization that these effects were produced. The induced currents declared a change of condition only, and they vanished the moment the act of magnetization or demagnetization was complete. The effects obtained with the welded ring were also obtained with straight bars of iron. Whether the bars were magnetized by the electric current or were excited by the contact of permanent steel magnets, induced currents were always generated during the rise and during the subsidence of the magnetism. The use of iron was then abandoned, and the same effects were obtained by merely thrusting a permanent steel magnet into a coil of wire. A rush of electricity through the coil accompanied the insertion of the magnet. An equal rush in the opposite direction accompanied its withdrawal. The precision with which Faraday describes these results and the completeness with which he defined the boundaries of his facts are wonderful. The magnet, for example, must not be passed quite through the coil, but only half through. For if passed wholly through, the needle, it is stopped as by a blow, and then he shows how this blow results from a reversal of the electric wave in the helix. He next operated with the powerful permanent magnet of the Royal Society, and obtained with it an exalted degree, all the foregoing phenomena. And now he turned the light of these discoveries upon the darkest physical phenomena of that day. Arago had discovered in 1824 that a disk of non-magnetic metal had the power of bringing a vibrating magnetic needle suspended over it rapidly to a rest, and that on causing the disk to rotate, the magnetic needle rotated along with it. When both were quiescent, there was not the slightest measurable attraction or repulsion exerted between the needle and the disk. Still, when in motion, the disk was competent to drag after it not only a light needle, but a heavy magnet. The question had been probed and investigated with admirable skill by both Arago and Ampere, and Poussin had published a theoretic memoir on the subject. But no cause could be assigned for so extraordinary an action. It had also been examined in this country by 2 celebrated men, Mr. Babbage and Sir John Herschel, but it still remained a mystery. Faraday always recommended the suspension of judgment in cases of doubt. I have always admired, he says, the prudence and philosophical reserve shown by M. Arago in resisting the temptations to give a theory of the effect he had discovered, so long as he could not devise one which was perfect in its application, and in refusing to assent to the imperfect theories of others. Now, however, the time for theory had come. Faraday saw mentally the rotating disk under the operation of the magnet, flooded with his induced currents, and from the known laws of interaction between currents and magnets, he hoped to deduce the motion observed by Arago. That hope he realized, showing by actual experiment that when his disk rotated, currents passed through it, their position and direction being such as must, in accordance with the established laws of electromagnetic action, produced the observed